Hello fellow sapiens, and welcome to Sleepless Homo, a quiet corner of the internet where science slows down. Whether you're preparing to sleep, cooking, driving, or just letting your mind wander through deep time, this is your moment to breathe, to think, to listen. Here we explore soft science, not wild speculation, but humble evidence told softly. If you appreciate calm storytelling and long-form knowledge, please like and subscribe. It helps this kind of quiet education reach more sleepless minds, people who still believe the world can be conquered with curiosity and understanding, not noise. Tell us in the comments, do you listen before bed, while working, or somewhere in between? And if you drift off during the story, I've left timestamps in the description so you can find your way back, because this story, from beginning to end, is worth hearing. And as always, stay curious, stay calm. Now, let's talk about why, 100,000 years ago, our species started running a race that never truly ended. For nearly 400,000 years, the world of stone was almost silent. Generation after generation chipped the same edges, struck the same angles, and handed the same shapes to their children. In Europe and Western Asia, the early Neanderthals perfected a single idea. Take a block of flint, carve a sharp edge, and keep carving it the same way for the next 20,000 winters. Across Africa, the ancestors of our own species were doing little different. The Achillean hand axe, teardrop-shaped, balanced in the palm like a thought that never aged, was passed from one mind to the next as if time itself had been paused. For all we can tell from the layers of soil and ash, there was almost no hurry in being human. Why did nothing change for so long? It is one of the quietest puzzles in prehistory. Modern eyes are drawn to progress, to sudden bursts of invention, to golden ages, but the long middle of the Pleistocene was a meditation on sameness. From roughly 400,000 to 120,000 years ago, the pace of human innovation was glacial. In caves scattered from Spain to the Levant, the stone artifacts of 1 century are indistinguishable from those 100 millennia later. A flake from France could be mistaken for one from Georgia. Both could have been struck by the same hand. At first glance, this looks like failure, the absence of imagination. But evolution rarely hurries unless it must. The slow rhythm of that age may tell us that, for once, the world was predictable enough for stability to be the winning strategy. When conditions remain familiar, change is costly. Mutation rates in hominins were steady, populations small, and each small group's knowledge pool limited. With only a few thousand individuals spread thinly across continents, cultural drift was almost a statistical impossibility. An idea born in one valley could vanish with its maker before ever reaching the next ridge. Archaeologists have tried to read this stillness through the language of tools. The Neanderthals' preferred technique, called the Levallois method, was an elegant geometry of patience. A stone core was shaped into a turtle shell dome, then struck once to release a perfect flake. The design maximised control and minimised waste. It also implied teaching, someone showing someone else how to do it, not just once, but forever. The very efficiency of the process may have been what kept it frozen. If a method works flawlessly, why change it? In Africa, roughly the same pattern held. The large hand axes and cleavers of the Achillean tradition persisted for hundreds of millennia. Only subtle refinements appear. Thinner edges, slightly straighter spines, a little more symmetry. There were no sudden leaps, no symbolic carvings, no delicate bone tools. The people making them, perhaps early Homo heidelbergensis, perhaps the first populations close to Homo sapiens, had brains almost our size, yet their material world moved at the tempo of erosion. We have to imagine what that meant in lived experience. A child learned to strike stone by watching an elder, whose gestures had been learned from another elder, back through a lineage of imitation stretching farther than memory. No drawings, no blueprints, just motion. A rhythm of hands, eyes, and sound. Tap, flake, rotate, repeat. Culture existed, but it was culture without acceleration. Part of the reason may lie in ecology. Between 400,000 and 120,000 years ago, much of the Old World offered relative abundance. Southern Europe was a mosaic of oak forest and grassland, rich with deer and horse. Africa's Rift Valley swarmed with antelope, zebra, and the slow reliability of migration seasons. For most hominins, daily life meant moving short distances, following predictable herds, gathering plants that sprouted in the same places year after year. There was no sudden catastrophe forcing new tools or strategies. Stability dulls invention. Another factor was energy. Innovation costs calories. To test, fail, and refine an idea requires time and food to spare. A small group living at subsistence threshold can rarely afford to experiment. It repeats what worked yesterday because hunger is a persuasive teacher. The archaeological record from sites like Boxgrove in England, dated around 500,000 years ago, shows butchery marks on horse bones made with beautiful precision, but always the same pattern, as if the memory of that technique had become ritual. Yet we know these people were not simple. Cut marks, hearths, and the spatial organisation of living areas hint at planning, cooperation, even empathy. In Spain's Cima de los Huesos cave, a deep shaft held at least 28 individuals, deliberately placed there around 430,000 years ago. Whether burial or disposal, it shows a collective decision, a group mind aware of loss. Intelligence was already present. What was missing was variation. Genetics adds another clue. When population size is tiny, evolution slows. Each generation offers few opportunities for new mutations to spread. The effective breeding population of all humans through much of the Middle Pleistocene may have been fewer than 10,000 individuals. That is roughly the population of a small modern town, dispersed over continents. Cultural information in such a sparse network behaves like heat in a vacuum. It dissipates. The brilliance of one artisan could be erased by a drought or a predator in a single night. The geological rhythm of the planet also kept resetting the board. Glaciers advanced and retreated, but not yet with the ferocity of the later ice ages. When environments change too slowly to kill but too frequently to settle, adaptation tends toward generalism. A generalist species survives by doing many things adequately, not one thing brilliantly. So, the hominins of this era became masters of adequate survival, omnivores with hands capable of everything but committed to nothing new. From our modern vantage point, the archaeological record looks like a long static screen interrupted by occasional sparks. Around 300,000 years ago, hints of regional styles appear. Bifaces in Africa become slightly smaller. In Europe, the Neanderthal refined the Levallois flake, but these are minor dialects in the same language of stone. The overall grammar of technology remains unchanged. Some researchers argue that innovation may have happened, but was lost. Perishable materials like wood, fibre or hide decay quickly. A clever woven net or a wooden spear thrower could vanish without fossil trace. Indeed, discoveries such as the wooden spears from Schöningen, Germany, dated roughly 300,000 years ago, suggest bursts of ingenuity that flickered and faded. They hunted, planned, perhaps even decorated, but the pattern never cascaded into cumulative change. It is possible that the constraint was social, not cognitive. In small bands, hierarchy and conformity can stifle novelty. If a new method threatens tradition or authority, it may be ignored. Cultural evolution depends not just on bright minds, but on receptive communities. The most dangerous sentence in prehistory might have been, "We've always done it this way." Still, to call this period stagnant misses something essential. It was an age of quiet mastery, not ignorance. These humans adapted perfectly to a world that asked for constancy. They tracked herds across continents, endured shifting climates, controlled fire for warmth and cooking, and maintained genetic continuity through endless cycles of scarcity and plenty. Their lives required knowledge deep enough to navigate landscapes without maps, seasons without calendars, and families without writing. The miracle is not that they changed so little, but that they survived so well. Every flint core buried in ancient soil is a fossilized conversation between competence and necessity. The absence of novelty tells us that for hundreds of thousands of years, our ancestors lived in ecological equilibrium. They were part of the world, not yet rewriting it. And perhaps that balance was the reason the spark of acceleration had to wait. Only when stability finally broke would the race begin. From a genetic perspective, evolution needs both mutation and selection pressure. Mutations were happening all along, the random rearrangements in DNA that occur every generation. But selection was gentle. There were few predators capable of challenging fully upright tool-using apes. Disease outbreaks may have been localized, climatic swings slow. Under such mild pressure, natural selection rewards reliability over innovation. Brains remained large but consistent. Bodies adapted slowly to regional climates. The same broad skulls, robust limbs and heavy brow ridges persisted for eons because they worked. When we look at a Neanderthal skull beside an early Homo sapiens one, the differences are subtle. A slightly higher forehead here, a smaller face there. In evolutionary terms, they are near twins. The real divide would come later, not in bone but in behaviour. During this long pause, nature was refining the hardware while waiting for the software to rewrite itself. Archaeologists often describe the Middle Pleistocene as the long apprenticeship. It was the period when the genus Homo learned endurance, the slow education of a species that would one day learn speed. The patience encoded in those millennia may even have laid the groundwork for future innovation. The coordination required to nap flint precisely is neurologically demanding. It builds fine motor control, attention, and planning circuits. These neural foundations may have been the quiet scaffolding on which later creativity would rise. If there is humour hidden in this stillness, it is the cosmic kind. Imagine a species rehearsing the same trick for 400,000 years before realising it could improvise. From the perspective of deep time, our later bursts of invention look almost manic, as if the universe pressed fast forward after an eternity of buffering. But that is the illusion of hindsight. For the people living then, each lifetime was as full as ours. Hunting, raising children, finding warmth, telling stories we can no longer hear. The absence of change in their tools does not mean an absence of meaning. Eventually, subtle signs of restlessness appeared. In Africa, stoneworkers began experimenting with smaller flakes, more intricate retouching, perhaps even composite tools with wooden handles. In Europe, the Neanderthals started preparing pigments, manganese dioxide, ochre, though we cannot know if it was for art or utility. These faint variations suggest minds beginning to test the boundaries of tradition. The long pause was fraying at the edges. What ended it? That question will echo through the rest of the story. Some combination of environment, population, and social complexity would soon tip the balance. But during this earlier epoch, the slowness itself was the adaptation. In a world that changed little, the surest path to survival was to remain the same. When we hold one of their hand axes in a museum today, polished smooth by time, we are touching the fingerprint of repetition. Proof that evolution sometimes practices patience before brilliance. Every perfect symmetry carved into stone was an act of faith that tomorrow would look like yesterday. They were right, for a very long time. And then, eventually they weren't. Could instability, not stability, make a species intelligent? Around 120,000 years ago, the Earth began to breathe unevenly. It was not a single catastrophe, not yet, but a pattern of wild oscillations that would last tens of thousands of years. The long, steady calm that had shaped the patient species of the Middle Pleistocene was ending. In its place came a world that refused to stay the same for more than a few human lifetimes. For early Homo sapiens and their close cousins, this was not just weather. It was the start of an unpredictable education in survival. At that time, vast ice sheets in the north pulsed like slow lungs, expanding and retreating with each flicker of the planet's orbital rhythm. What scientists now call marine isotope stage 5 began with relative warmth, forests spreading northward, seas swelling, rainfall returning to deserts. But the Earth's orbit is not steady. It tilts, wobbles, and stretches over cycles measured in tens of thousands of years, shifting sunlight between hemispheres. These small astronomical changes, Milankovitch cycles, turned gentle warmth into violent instability. Between 115 and 80,000 years ago, the planet swung from near-tropical phases to biting cold in less time than it takes a species to adapt. For people living through it, the signs would have been visceral. Grasslands turning to sand, lakes shrinking into salt flats, rivers roaring and then vanishing, glaciers surging southward across lands that had been green for generations. In the cores of ancient ice from Greenland and Antarctica, we can still see these changes written like tree rings. The trapped air bubbles record abrupt temperature shifts of 10 degrees in mere centuries. Dust layers thicken, then thin, marking the world's erratic breath. Across Africa, where our species was gathering its strength, this meant relentless migration. Once lush corridors like the Saharan Greenbelt, fed by monsoons, began drying into a mosaic of isolated oases. Herds of antelope and gazelle followed shrinking grasslands, and humans followed them. In the caves of southern Africa, at sites such as Pinnacle Point and Blombos, archaeologists have found traces of shellfish gathering, pigments, and hearths that appear and disappear in rhythm with these environmental pulses. When the coastlines flooded during warmer phases, people retreated inland. When the sea withdrew during cold phases, they returned, exploiting new landscapes. Every few thousand years, survival demanded an entirely new playbook. In Europe and Western Asia, the story was harsher. Neanderthals, who had thrived in temperate woodlands, found themselves trapped between ice and steppe. Forest died back, replaced by treeless plains. Mammoths and woolly rhinos roamed where deer once grazed. For a species adapted to ambush hunting in forests, the open tundra was both opportunity and exile. Bones from sites like La Ferracie and Crapena show patterns of stress, injury, and nutritional strain. Populations fluctuated as fast as glaciers advanced, with local groups blinking in and out of existence like short-lived experiments. These weren't steady pressures, they were moving targets. Evolution thrives on consistency. But what happens when the environment changes faster than biology can follow? For the first time, perhaps, flexibility itself became an adaptation. The individuals who could notice change earliest, who could improvise, move, and teach others, left more descendants. Intelligence began to mean not just knowing, but unlearning and relearning. In this context, the mind itself becomes a form of climate resilience. Think of it as mental plasticity selected by chaos. A brain capable of connecting pattern to memory, of anticipating the unpredictable, has a survival advantage when the map keeps redrawing itself. Some anthropologists describe this period as the crucible of behavioural adaptability, the moment when culture, still simple and local, began to matter more than genetics. The archaeological record supports this gradual shift. In Eastern Africa, toolkits diversified. Stone flakes became smaller, more specialised. Microscopic analysis of residues shows experimentation with different raw materials. Quartz, chert, obsidian, each chosen for particular tasks. Evidence from sites such as Olorgesailie in Kenya suggests early exchange networks, where materials from distant sources appear together, implying travel or trade routes spanning hundreds of kilometres. These may have been born from necessity, as groups sought resources increasingly scattered by climatic swings. Yet they hint at the first fragile webs of interconnection that would later define our species. Meanwhile, the ice advanced. Around 110,000 years ago, temperatures plunged again. Glaciers crept outward from Scandinavia and Canada, locking up so much water that sea levels fell by tens of metres. Coastlines expanded, revealing vast new plains, but these were barren and cold. Africa's lakes shrank. The Nile faltered. The corridor that had once linked sub-Saharan populations to the Mediterranean world became a desiccated wall of sand. Populations retreated southward into ecological refuges, small pockets of stability near coasts and highlands, where food and water remained predictable. This pattern of contraction and expansion repeated over millennia. Genetic models suggest that human populations during these oscillations were fragmented into semi-isolated groups, sometimes separated for thousands of years, sometimes reconnecting when conditions eased. Such fragmentation, paradoxically, can accelerate diversity. Each small group adapts in its own way, experimenting culturally even when biological evolution remains slow. When they meet again, ideas recombine faster than genes. It is tempting to imagine these encounters, two groups meeting after centuries apart, exchanging stories in gestures and glances, comparing tools, learning new methods of hunting or shelter building. Each merger is a small cognitive revolution. The instability that drove them apart also guaranteed novelty when they met again. On a global scale, these oscillations shaped every continent differently. In the Levant, fluctuating rainfall turned fertile plains into deserts and back again, alternately inviting and repelling waves of human and Neanderthal occupation. In South Asia, monsoons grew erratic, flooding one decade and failing the next. In China, loose plains alternated between steppe and forest, influencing the movement of early Homo sapiens eastward. Everywhere, the rhythm was the same: adaptation through motion. From a geological perspective, this period marks the transition between marine isotope stage 5 and stage 4, a shorthand for the ratio of oxygen isotopes in marine sediments that track global temperature. Beneath that technical label lies a simple truth. The Earth was beginning to tremble with unpredictable energy. Within 10,000 years, average conditions could shift from interglacial warmth to glacial chill. For species bound tightly to local ecologies, that volatility was lethal. For a species learning to think abstractly, it was opportunity. We sometimes imagine intelligence as a luxury, a flowering of art and philosophy, but here it was pure pragmatism. The hominins who survived these centuries of turbulence did so because they learned to plan beyond the present. A campfire needed fuel not just for tonight, but for the next unexpected cold snap. A waterhole was not a fixed point, but a probability. The ability to anticipate, to imagine futures that did not yet exist, may have been born from this instability. Archaeological sites such as Sibudu Cave in South Africa show layers of occupation that rise and fall in step with climate curves. Periods of abundance leave thick strata of ash and tools. Dry periods leave silence. When people returned, their technologies had shifted slightly. New adhesives for hafting, different hearth structures, more refined organisation of space. The pattern suggests that humans were not passive victims of climate, but responsive innovators, using each disruption as a lesson. The biological record echoes this story. Fossils from Jebel Irhoud in Morocco and Homo kibish in Ethiopia, both around this time frame, show early Homo sapiens with modern features but regional variation, signs of a species stretching its range and experimenting with form. Though the genetic details of this diversification remain uncertain, it fits a world in motion. Migration under stress forces recombination, spreading traits across vast distances. Diversity itself becomes a survival strategy. If we could step into that world, it would not feel like a single age but a collage of climates. In one region, humid savannas buzzed with life. A few hundred kilometres away, dust storms scoured the earth. Humans existed in patchwork time, their lifeways constantly recalibrated to the local mood of the planet. It was a laboratory without control groups, and intelligence was the experiment's byproduct. As we trace these patterns today through ice cores, pollen data, and isotopic signatures, we see that instability can be as creative as catastrophe. Evolutionary theory often emphasizes adaptation to steady selection pressures, cold, drought, predation. But what if the greatest teacher is unpredictability itself? A species that can learn to stay flexible amid chaos, may eventually transcend the pace of genetic change. Cultural memory becomes the new inheritance, and it updates faster than DNA. By 80,000 years ago, the climatic pendulum had not yet found rest. The great ice sheets were still growing, the deserts still widening. But somewhere within these oscillations, our species had begun to treat instability not just as threat, but as norm. The toolkit of the later Middle Stone Age reflects that attitude. Modular, adaptable, portable, tools small enough to carry between habitats, shelters light enough to rebuild elsewhere, knowledge flexible enough to reapply under different skies. It is humbling to realize how recent this awakening is. For millions of years, life evolved by staying still long enough for natural selection to sculpt it. Then, within a few hundred millennia, the Earth's climate began changing too fast for slow evolution to keep pace. Homo sapiens emerged precisely in that window, not in the quietest era, but in one of the most volatile. We are in a sense children of instability. Scientists still debate how direct the link is. Some caution that correlation is not causation, that cognitive advances could have unfolded regardless of glacial pulses. Perhaps we were already capable of innovation, and climate merely provided the stage. But the alignment between environmental turmoil and behavioural complexity is difficult to ignore. Every data layer we uncover seems to show the same rhythm: chaos outside, creativity inside. When we imagine intelligence arising, we often picture a spark, but perhaps it was more of a tremor. The planet shook, rivers moved, and minds began to notice patterns in the noise. Survival depended on prediction, and prediction is the seed of thought. From then on, every shift in temperature, every migrating herd, every flood and famine would whisper the same lesson. The world is never finished, so neither can we be. Even now, the fossils from that era carry silence between them. We see the artifacts, but not the faces, not the confusion or the sudden insight of realizing that yesterday's path no longer led to water. What we can say, with humility, is that the instability of those 40,000 years forged a habit of adaptation that defines us still. We became, through necessity, the species that expects change, and perhaps that expectation, born under a sky of shifting clouds and moving ice, was the first step toward the restless intelligence that would one day remake the planet itself. Did one eruption nearly reset our species? 74,000 years ago, the planet drew in a long volcanic breath and exhaled darkness. On the island of Sumatra, a caldera nearly 100 kilometers wide tore open the Earth's crust, releasing more than 2,000 cubic kilometers of ash and molten rock into the sky. What we call the Toba super eruption remains one of the largest volcanic events known in the last 2 million years. For months, perhaps years, the atmosphere thickened with aerosols. Sunlight dimmed to a ghostly twilight. The world cooled. For the small populations of humans then scattered across Africa and Asia, this was not myth or metaphor. It was a test of endurance against the raw mechanics of the planet. From ice cores drilled deep into Greenland and Antarctica, scientists have read the faint chemical echoes of that eruption. Spikes of sulfuric acid, layers of trapped dust, isotopic signatures of abrupt cooling. These signals tell us that Toba injected enough material into the stratosphere to reduce global temperatures by several degrees. Some estimates suggest a volcanic winter lasting 6 or more years, followed by a century of disrupted climate. In simple terms, the sky itself became unpredictable. The eruption's immediate reach was staggering. Across the Indian Ocean, ash fell like grey snow. In parts of India and the Bay of Bengal, layers up to 15 centimetres thick still mark the event today. Wind carried finer particles westward across Arabia and Africa, settling over grasslands where small bands of Homo sapiens hunted and gathered. Even the oceans dimmed under the haze. Reduced sunlight slowed photosynthesis in surface plankton, rippling through the food chain. The event was global, but its effects were uneven. Some regions suffered deep cold and drought, others only a brief dimming. Geography determined fate. For decades, scientists believed this eruption nearly wiped us out. Early genetic models of human diversity seem to show a severe population bottleneck around this time. Perhaps only a few thousand individuals surviving in isolated refuges. It was a dramatic story. One volcano reducing humanity to a near-extinction event. The Toba catastrophe hypothesis, as it became known, fit the evidence we then had. A thin layer of ash across continents, low genetic variation among modern humans, and hints of climatic chaos. It was an elegant narrative, maybe too elegant. Over the last 20 years, that picture has changed. Excavations in India, Africa and Southeast Asia have revealed human sites above and below the Toba ash layer showing continuous occupation. Stone tools found at Jwalapuram in southern India, identical in technology both before and after the eruption, suggest that local populations endured the fallout. At Pinnacle Point in South Africa, evidence of hearths, shell middens and ochre yews shows no sudden break in human presence. In Sumatra itself, near the heart of the eruption, forests eventually recovered and fauna returned within a few centuries. The planet healed faster than our early models imagined. This does not mean it was easy. A veil of ash covering vegetation would have stripped landscapes bare for months. Streams and lakes would have turned acidic. Animals would have migrated or died. But survival is not about comfort. For small mobile bands of humans, flexibility was already a way of life. They could move toward coasts, exploit marine resources, or retreat into refuges where rainfall and vegetation persisted. Rather than an apocalypse, Toba may have been a filter, eliminating the least adaptable while favouring groups already skilled in coping with change. We cannot know what it felt like to witness such skies. Perhaps there were weeks when the sun was little more than a red disk at noon, when ash turned rivers grey and mornings carried the taste of sulphur. Yet even in that dim world, fire still burned. The same volcanic ash that poisoned some lands enriched others. As it settled, minerals leached into soils, rejuvenating ecosystems in the decades that followed. The Earth, in its violent way, was also preparing the ground for renewal. From a climatic standpoint, Toba's cooling was significant but not unique. Other volcanic events have caused short-term temperature drops. The eruption of Mount Tambora in 1815, for example, produced the year without a summer. What made Toba exceptional was scale and duration. But geological evidence suggests that global cooling after the eruption, while severe, did not plunge the planet into instant ice age. Instead, it likely amplified an already developing glacial trend. Humanity was caught in the middle of a slow descent into colder times, and Toba simply steepened the slope. Paleo-environmental data from East Africa shows a complex pattern. Lake levels fluctuated, rainfall decreased in some regions but increased in others. In the Indian subcontinent, sediment cores revealed dry conditions lasting centuries, yet coastal ecosystems remained resilient. Such variation may explain why our species endured. Diversity in habitats meant diversity in strategies. Some groups may have collapsed, others thrived in unexpected refuges. The genetic bottleneck might reflect regional contractions rather than a single global crash. It is also possible that the bottleneck signature arises from later events, subsequent migrations or founder effects as small groups colonize new areas. In other words, the story of Toba as a singular near extinction may be an echo of our tendency to seek neat causes. Nature rarely provides them. Evolution operates through layered contingencies, climate, geography, chance, and the stubborn persistence of living things. Still, the eruption left a psychological scar in the scientific imagination because it reminds us how thin our margin is. A few degrees cooling, a few years of darkness could have erased us. It did not. And that fact, our survival, deserves as much attention as the catastrophe itself. Somewhere in those ashen decades, humans proved that adaptation was no longer just biological. It was behavioural. The archaeological traces hint at this quiet resilience. At Middle Stone Age sites in southern Africa, hearths reappear shortly after the estimated eruption period, layered with new sediments that show continued habitation. The shells of edible mollusks, still abundant in these layers, imply that coastal foraging buffered food shortages inland. In India, microscopic analysis of soil above the ash shows renewed vegetation within decades, suggesting that humans who had fled returned once grasses and game recovered. We can almost picture them stepping back onto familiar ground, the air still smelling faintly of sulphur, and rebuilding the routines that kept them alive. For volcanologists, Toba is also a lesson in the limits of our measurements. Dating methods have margins of error. Climate models depend on assumptions about particle size, aerosol residence time, and solar radiation balance. Even with satellite sensors and supercomputers, predicting the outcome of a future super eruption remains uncertain. For paleoanthropologists, the uncertainty is deeper. What we read as absence of evidence might be evidence lost, sites eroded, artifacts buried beyond reach. Each new discovery slightly rewrites the magnitude of the event. Humility is the only honest stance. The truth may lie between catastrophe and continuity. Perhaps Toba fractured populations but did not destroy them, scattered groups but spared enough to rebuild. The important point is that by surviving such a planetary crisis, Homo sapiens demonstrated a resilience that earlier hominins might not have matched. Mobility, cooperation, and an ability to exploit varied diets became our shield against extinction. The planet threw one of its hardest tests, and the species bent but did not break. In the centuries after, the Earth's systems slowly rebalanced. Vegetation reclaimed the grey plains, rivers cleared, animals returned. The sky brightened. Life resumed its intricate negotiations. If any oral memory of the event lingered, if stories of the years without sun were ever told, they are long gone. Yet in the genes of our descendants may remain subtle marks of that bottleneck, a whisper of how few we once were and how close we came to silence. There is something quietly profound in knowing that our ancestors survived not through strength, but through patience. They endured a world that stopped making sense and waited it out. In that endurance lies a lesson for every age that follows. Intelligence begins with survival, and survival often means humility before forces larger than comprehension. Today, Toba's caldera is filled with a deep blue lake, calm and deceptive. Tourists take photos on its rim, unaware that beneath the surface lies the memory of planetary winter. Scientists sample its sediments to reconstruct what happened, grain by grain. What they find is not a record of apocalypse, but of recovery. Ash turns to clay, life returns, ecosystems reset. The story of Toba, seen clearly, is not one of extinction but of persistence. When we ask whether one eruption nearly reset our species, the answer is both yes and no. It shook the ecological web hard enough to prune it, but left enough branches intact for life to keep climbing. For humans, it was a rehearsal for the challenges ahead. Droughts, ice ages, migrations, the same traits that carried us through the ash, adaptability, cooperation, memory, would later define our expansion across the world, and perhaps that is the most important legacy of Toba. It taught us, in a language of dust and silence, that fragility and resilience are not opposites but partners. A species aware of its vulnerability is one that learns to prepare, to imagine, to adapt. In that dim, volcanic twilight, humanity's endurance was tested, and quietly it passed. What if the greatest evolutionary rival wasn't outside us? For most of life's history, evolution works like a long chase scene. Predators sharpened their claws, prey grew thicker hides or learned to run faster. Parasites changed their tactics, immune systems countered in kind. It was an endless cycle of adaptation where no species could afford to stop moving. The evolutionary biologists who first recognized this pattern borrowed a line from Lewis Carroll's Through the Looking Glass, where the Red Queen tells Alice, "It takes all the running you can do to stay in the same place." That line became a metaphor for the relentless pace of natural selection. But somewhere in our own lineage, the chase took a strange turn. Around 100,000 years ago, humans began to make their fiercest competitors not lions, not climate, but one another. The Red Queen hypothesis began as a theory about survival. Every species evolves under pressure from others, hunter versus hunted, virus versus host. The game never ends because every advantage creates a new countermeasure. In this race, success is temporary. What made humanity different was the point at which we stopped racing against nature and started racing within our own species. Once our ancestors became each other's primary selective pressure, the rules of evolution changed. The weapons were no longer claws or speed, but perception, memory, and strategy. To imagine this shift, we need to picture a world where intelligence itself becomes an arms race. Each improvement in awareness demands an equal improvement in others just to keep balance. If your neighbour learns to plan better hunts, you must learn to anticipate them. If one group becomes more skilled at resource gathering, another must become better at sharing or stealing. Over generations, cognition starts spiralling upward, not toward perfection, but toward constant adjustment. In evolutionary terms, this is called frequency-dependent selection. When the value of a trait depends on what everyone else is doing, a bigger brain isn't inherently better unless the others have them too. Then it becomes a requirement. The fossil record can't show us this arms race directly, but it leaves hints. By around 100,000 years ago, brain size in Homo sapiens stabilized near its modern volume. Yet within that capacity, internal organization was shifting. Endocasts show subtle changes in the frontal and parietal regions, areas tied to attention and executive control. More neurons meant more potential for anticipation and manipulation, but also more metabolic cost. The brain consumes enormous energy, so evolution would only have favoured such expansion if the payoff was survival through smarter behaviour. If the threats of predators were waning, the remaining challenge had to come from interactions within our own kind. Every act of cooperation contains the seed of competition. To live in groups is to balance trust and deception, altruism and self-interest. Game theorists studying modern human behaviour often model this as an iterative prisoner's dilemma. When individuals repeatedly interact, they learn to detect cheaters and adjust strategies. Over time, the best survivors are not the strongest or the fastest, but those most skilled at predicting the motives of others. We call this the social intelligence hypothesis, the idea that navigating social complexity drives cognitive evolution, but underneath it lies the logic of the Red Queen. Once success depends on understanding other minds, every improvement forces new ones to arise. It is easy to romanticize cooperation, but evolution is pragmatic. Generosity is useful because it builds reputation. Reputation is useful because it secures allies. In small groups of hunter-gatherers, one selfish act might cost a life, yet one act of excessive trust might cost survival. The balance is delicate. Those who learned to read intentions accurately, to sense loyalty, to judge fairness, to predict betrayal, had a measurable edge. Over thousands of generations, this feedback loop refined our ability to infer thoughts and emotions that we cannot see. Out of that came something resembling theory of mind, the capacity to imagine what others think. Once that skill appeared, it became impossible for evolution to ignore. Here, the Red Queen's race accelerates. To deceive effectively, you must first understand belief. To detect deception, you must understand the limits of another's knowledge. Each layer builds on the last. Eventually, minds evolve not only to outwit, but to anticipate being outwitted. Intelligence becomes recursive, an awareness of awareness itself. The benefit of this recursion is flexibility. The cost is anxiety. A species constantly modelling what others might do also imagines what others might think of itself. Consciousness begins to loop. When biologists apply the Red Queen model to human evolution, they often focus on sexual selection, competition for mates rather than survival. In many species, displays of fitness become exaggerated under such competition. The peacock's tail, the stag's antlers. For humans, display shifted inward. Wit, creativity, and memory became courtship traits. The brain turned into its own ornament, broadcasting genetic quality through ideas, humour, and problem-solving. If being clever improved reputation and reproductive success, then cleverness itself became a target of selection. In that sense, intelligence was not an accidental byproduct of survival. It was sexually and socially sculpted. The archaeological timeline supports this shift indirectly. By 100,000 years ago, human populations were small but increasingly interconnected. Contact between groups brought opportunities for exchange, but also for competition over resources and prestige. The need to maintain alliances while guarding territory would have intensified cognitive demands. A species that once relied on instinct now relied on negotiation. Each campfire became a microcosm of the Red Queen's court, a place where reputation mattered, where stories could elevate or destroy, where memory of favours and betrayals defined hierarchy. Importantly, this kind of evolution doesn't necessarily produce happiness. A world where everyone competes cognitively is also one where stress and vigilance rise. The same neural machinery that predicts danger also predicts social consequences. From an adaptive standpoint, mild paranoia may have been useful. The brain evolved to track social debts as carefully as food supplies. We became creatures haunted not only by hunger, but by opinion. That trait, once essential, still shapes human psychology today. The Red Queen framework also helps explain why technological change, once it began, accelerated so rapidly. Every new tool or tactic altered the balance between individuals and groups, demanding counter-strategies. Yet before that explosion, the same principle played out invisibly in minds. Innovation does not appear out of nothing, it germinates in competition. The first sparks of creative thought may have been small advantages, new ways of hunting, new uses of fire. But behind each lay a mental contest to stay relevant in a social world that rewarded novelty. From a genetic perspective, such intraspecies selection is powerful. Traits influencing brain function, synaptic plasticity, learning rate, memory retention can spread quickly if they provide social leverage. But the Red Queen ensures that equilibrium never lasts. As soon as everyone can learn faster, the advantage disappears. Evolution keeps running, not toward a finish line but toward the next equilibrium. The only constant is acceleration. This concept can feel unsettling because it reframes progress as a treadmill. Intelligence didn't make life easier, it made it more complicated. Each gain created new expectations. Once we learned to plan, we had to plan better. Once we could imagine the future, we had to fear it. The same adaptability that saved us from extinction also locked us into perpetual motion. Even our species' capacity for reflection, this very attempt to understand the pattern, is part of the race. To stop thinking about how to think would mean falling behind. Biologists studying microbial systems sometimes use computer models to demonstrate red queen dynamics. When two populations co-evolve, say, bacteria and viruses, the rate of genetic change increases in both. Remove one, and the other slows down. It's tempting to see a similar pattern in human history. Our rate of cultural and cognitive change exploded once the main opponent became ourselves. Nature set the stage. Competition within the species wrote the script. Yet we should be cautious about turning the Red Queen into myth. Evolutionary metaphors are powerful, but the data behind them are always partial. We cannot extract motives from fossils. We can only infer patterns from comparative biology, genetics, and behavior. The theory fits, but like all scientific models, it simplifies. Reality is untidy. Intelligence likely emerged from multiple overlapping pressures: ecological unpredictability, group living, sexual selection, and cumulative learning. The Red Queen is one thread in a tangled web. Still, it helps us glimpse why our cognition is both remarkable and restless. If we step back, the metaphor gains a quiet poetry. The Red Queen runs not to win, but because standing still means extinction. That is also the story of us. The arms race that once unfolded between predators and prey now unfolds in conversation, in memory, in the subtle exchange of understanding. Our ancestors didn't need to conquer the planet to start this race. They only needed to compete for comprehension. The battlefield moved inside the skull. Around 100,000 years ago, as the climate stabilized briefly after millennia of chaos, our species might have felt the first effects of this inner acceleration. Survival no longer depended solely on endurance against the elements, but on adaptability within communities. The greatest evolutionary challenge was not mastering nature, but navigating each other. Intelligence turned from a tool of survival into a condition of existence. And if the Red Queen is still running today, it is because we inherited her rhythm. Every innovation, every idea, every attempt to outthink the world keeps the race alive. But unlike the creatures before us, we can look over our shoulders and see her shadow, following close behind, reminding us that the contest never truly ends, it only changes form. How do you speedrun evolution without breaking the hardware? Somewhere between 90,000 and 70,000 years ago, something subtle but extraordinary was happening inside the skulls of our ancestors. The story isn't written in stone or pigment, but in the hollow echoes of bone, endocasts, the internal moulds of ancient crania that preserve the negative space where thought once lived. Those impressions tell us that the human brain, already large by primate standards, underwent a final quiet growth spurt. Within a geological blink of time, roughly 10% was added to its volume. That may not sound dramatic, but in evolutionary terms it was almost reckless. For a species already pushing the limits of childbirth, metabolism, and coordination, the expansion represented a high-risk bet. That bigger thinking would pay for its cost in calories and danger. Fossils from Africa, the Middle East and Asia help us trace this transformation. Skulls from Homo kibish, Jebel Irhoud, and Haerto show a gradual rounding of the cranial vault, a shortening of the face, and the emergence of what paleoanthropologists call a globular brain case, the shape that defines modern humans. Earlier hominins like Homo erectus and the first Neanderthals carried long, low skulls, their brains stretched backward like ovals. The new form is more spherical, a sign that internal architecture was shifting. The parietal and temporal regions expanded, accommodating areas linked with sensory integration and abstract reasoning. This was not just more brain, but differently arranged brain. The costs were immense. A newborn human's head now approached the maximum width that a pelvis could allow, without redesigning the entire reproductive system. Obstetrics became a compromise between the opposing demands of locomotion and cognition. The solution nature found was premature birth. Humans are born earlier in their developmental schedule than other primates, with brains still unfinished, soft and rapidly growing after birth. The result is a long period of dependency, but also plasticity. A brain that continues developing outside the womb can adapt more flexibly to its environment. Evolution traded risk for learning capacity. Endocast studies by researchers such as Philip Gunz and colleagues show that between 90 and 70,000 years ago, these structural refinements accelerated. The frontal lobes, seat of planning and inhibition, expanded relative to overall size. The parietal regions, integrating vision, touch, and spatial reasoning, ballooned. Together they form what neuroscientists sometimes call the frontoparietal network, a system associated with attention control, working memory, and the fluid intelligence that allows problem-solving in new contexts. While we cannot see thoughts fossilized, we can trace the scaffolding that made them possible. Why this happened then remains an open question. Climate instability continued, but that had been true for hundreds of millennia. Population densities were low, perhaps too low for random drift to explain the change. Instead, molecular genetics points to a subtler mechanism, the rapid turnover of regulatory genes influencing brain development. Certain sequences in our genome, ASPM, microcephalin, and a region called HOR1, show signs of strong positive selection during this window. They act not like blueprints, but like timing devices, coordinating the rate at which neurons proliferate and connect. A small tweak in these switches can shift the final architecture of the brain without altering its gross size. Take ASPM, short for abnormal spindle-like microcephaly associated. Mutations in this gene today cause drastically reduced brain volume, often less than half the normal size, yet without corresponding deformities in other organs. That precision suggests that during evolution, selection on ASPM fine-tuned neurogenesis, the production of neurons during embryonic development. Around 85,000 years ago, a new variant swept through human populations. We cannot know exactly what advantage it provided, but its rapid spread implies a significant one. Microcephalin tells a similar story. Its function overlaps with ASPM in controlling the cell cycle of neural progenitors. One particular lineage of the gene appears to have arisen about 37,000 years ago, another perhaps closer to the period we're exploring. Both show patterns of selection inconsistent with neutrality. Combined, they hint at ongoing optimization of brain growth, possibly balancing larger size with energy efficiency or structural stability. In a sense, evolution was learning to manage the expanding hardware, to make thinking scalable. HAR1, the human accelerated region 1, adds another layer. It is not a protein coding gene, but an RNA sequence that guides the folding of the developing cerebral cortex. When researchers compared humans and chimpanzees, they found only 2 changes in chimp-HAR1 relative to chicken, but 18 in the human version. A burst of mutation concentrated in a single tiny locus. This acceleration likely predates our timeline, but may have continued fine-tuning as other developmental genes joined the cascade. CHAR1 acts during the formation of caudal-retzius neurons, which orchestrate cortical layering, the blueprint for 6 layered human neocortex. Those layers are where our higher cognition lives. All of this sounds clean in retrospect, but evolution is a messy engineer. A larger, more complex brain meant longer childhoods, increased maternal mortality, and ever greater nutritional demands. The metabolic cost of our brains is astonishing. About 20% of resting energy for only 2% of body mass. To sustain that appetite, early humans needed reliable sources of fat and protein, which likely pressured them toward cooperative hunting and broader diets. Biology forced behavior to adapt, even before culture as we think of it existed. What makes this period remarkable is its speed. A 10% increase in average brain volume within roughly 20,000 years translates to an evolutionary rate an order of magnitude faster than the preceding 500,000 years. Something was pushing hard. Whether that force was ecological challenge, internal competition, or demographic change, we can only infer. but the fossil and genetic evidence agree that human brains during this window were under selection pressure unlike any before. It is as if nature decided to overclock cognition, pushing performance to the edge of what the body could sustain. One hypothesis is that this final burst of encephalization was self-reinforcing. Once brains reached a certain threshold of flexibility, they began creating problems only brains could solve. Toolmaking, migration, and complex cooperation would have increased the returns on intelligence, feeding a cycle where smarter individuals survived and reproduced slightly more. Over millennia, even tiny advantages compound. The result is not a linear improvement, but an accelerating one. The neuroanatomy bears out the consequences. Alongside enlargement, the internal wiring became denser. White matter tracts connecting frontal and temporal areas thickened, allowing faster communication between perception and planning. The corpus callosum, bridging the hemispheres, expanded. Such changes don't show up in fossil bone but can be inferred from comparative endocranial shape. They indicate a shift toward integration, a brain optimized for cross-modal synthesis rather than isolated functions. It could combine sight, sound, and touch into unified representations, the foundation for imagination. Even the microstructure of neurons evolves subtle differences. Modern humans have a higher ratio of small, fast-firing pyramidal cells in the prefrontal cortex compared to other primates. These cells allow fine-grained control and parallel processing but require stable metabolic support. Glial cells, once considered mere scaffolding, increased in number to maintain this neural storm. The brain was becoming not just larger, but more balanced, capable of sustained complex thought without burning itself out. Yet for all its sophistication, the expansion reached a ceiling. Since about 30,000 years ago, average brain size has actually decreased slightly. Many scientists think this reflects efficiency gains, streamlining circuitry rather than adding bulk. The earlier surge may have been a period of trial and error, building redundancies that later refinement could prune. The skull tells the story of both ambition and adjustment. Evolution rarely leaves perfection, it leaves survivors. When we study these transformations today, we must remember the limits of our evidence. Fossil endocasts are not blueprints. They capture outer contours, not inner thoughts. Genes like ASPM or HAR1 don't encode intelligence directly. They regulate processes whose downstream effects we barely understand. The temptation to link a single mutation to creativity or consciousness is strong but simplistic. Brains are emergent systems. Selection acts on function, not foresight. The line between adaptation and accident is often invisible. Still, the convergence of evidence points to a critical conclusion. By 70,000 years ago, our species carried a brain both biologically mature and dangerously ambitious. Its architecture allowed rapid learning, memory consolidation, and long-term planning. It could simulate futures, juggle variables, and hold contradictions. All of this emerged under pressure, not from comfort, but from constraint. Each improvement came with risk, every neuron purchased with energy and complexity. The mind that would one day invent art and language was first a machine for endurance. Perhaps that is the paradox of our design. Evolution pushed us toward intelligence not as a gift, but as a necessity. Bigger brains were expensive. Failure was fatal. Those who balanced the costs survived, and in doing so they inherited the most demanding organ nature ever built. Even now, the human brain feels both overpowered and fragile, capable of solving cosmic equations, yet vulnerable to exhaustion, hunger, and grief. It is hardware born from crisis, tuned by pressure, forever one mutation away from collapse. When we ask how evolution could run so fast without breaking the system, the answer might be that it nearly did. The limits of childbirth, energy, and coordination define a narrow window in which intelligence could expand. Too small a brain, and thought stagnates. Too large, and the species cannot reproduce. Humanity walks that knife edge still. Our brilliance exists because evolution gambled on risk and somehow won. And though we now peer back across those 70,000 years with MRI scanners and genome databases, the truth remains humbling. We do not fully understand how the 3 pounds of tissue inside our skulls became what they are. We can trace the milestones, the genes, the shapes, the timings, but not the leap from structure to awareness, That mystery sits behind every fossil, every sequence of DNA, whispering that some parts of our origin may always remain beyond measurement. The only certainty is that it happened under pressure, and that we are still living proof of its success. When did sentences start looping inside themselves? Somewhere between 100,000 and 60,000 years ago, a quiet revolution unfolded, not in tools or bones, but in the invisible circuitry of the human brain. The capacity for language, already forming in the airless corridors of our ancestors' minds, began to take shape as a system capable of infinite recursion. It was not the first time a creature had communicated. Many animals could already signal danger, beg for food, or announce territory. But what began inside Homo sapiens was different. It was not communication as reaction. It was communication as construction. The ability to nest one idea within another, to imagine events beyond the present moment, and to share them with others through sound and structure. It was the beginning of syntax, and with it, the beginning of thought as we now understand it. To trace this emergence, we have to look at the anatomy of the speaking brain. In modern humans, two regions dominate the linguistic landscape: Broca's area, in the left frontal lobe, and Wernicke's area, in the posterior temporal cortex. Broca's area manages speech production and grammatical sequencing, the architecture of phrases, while Wernicke's area interprets meaning and context. These regions exist in other primates too, but in humans they are connected by an exceptionally thick bundle of white matter fibers called the arcuate fasciculus. This neural highway allows ideas shaped in one region to be rapidly structured and vocalized in another. The precision of that connection, and its asymmetry between hemispheres, seems to have crystallized during this window in deep time. Endocasts from early Homo sapiens show subtle expansions of the inferior frontal gyrus, the surface marker of Broca's region, hinting that the biological foundations of complex grammar were already being laid tens of millennia before the archaeological record began to reflect it. What would it have felt like for a mind to cross that threshold? Before language became recursive, internal thought was probably limited to short sequences, images, sensations, emotional cues. The ability to link clauses to embed because and if turned that chain of impressions into narrative. A person could now think, if I go there, they might be there, or she knows that I know. This self-referential quality changed not only how people spoke, but how they reasoned. Recursive language creates recursive minds, thoughts about thoughts, plans within plans. The grammar of speech became the grammar of cognition itself. Modern neuroscience hints at how this transformation might have happened. The prefrontal cortex, already expanding from earlier evolutionary stages, became more specialized in sequencing actions and inhibiting impulses. Neural imaging of living humans shows that Broca's area activates not only when speaking, but also when processing hierarchical structures in music, mathematics, and problem-solving. That suggests its original function may have been broader, organizing sequences of behavior long before words arrived. Language may have co-opted a system built for planning. Under evolutionary pressure, that planning became vocal, allowing individuals to simulate events aloud, to rehearse outcomes with others before acting. Another clue lies in the FOXP2 gene, sometimes misleadingly called the language gene. All vertebrates possess versions of it, but two critical mutations unique to modern humans appeared sometime in the last 200,000 years, probably within this same linguistic window. FOXP2 regulates networks involved in motor control of the mouth and larynx, as well as neural plasticity in corticostriatal circuits. Its presence alone doesn't create language. Neanderthals also carried the modern variant, but it enables the fine control and feedback necessary for fluid articulation. When combined with expanded cortical association areas, it turned vocalization into precision instrument. Speech could now carry not just emotion, but syntax, the spine of meaning. In this era, the most profound change was probably silent. Long before structured language echoed across the savannah, inner speech began to take hold. Once the brain could simulate words internally, it gained a private rehearsal space for behavior. Planning no longer required trial and error, it could unfold inside the skull. Cognitive scientists call this mental time travel. the capacity to imagine future scenarios and adjust strategy without external cues. It is, in essence, thinking in sentences. The recursive loop of if-then statements allowed the brain to predict consequences and to test them in imagination before committing to action. In a dangerous, fluctuating world that was an evolutionary superpower, this internalization also opened the door to deception. The same circuits that let one model the future allowed one to model the minds of others. If I can imagine what you think I will do, I can choose to act differently. Lying, persuasion, and bluffing all rely on recursive thought. Linguists such as Noam Chomsky have long argued that recursion, the ability to embed clauses endlessly, is the defining feature of human language. Whether it arose gradually or as a threshold leap remains debated, but either way, its consequences were immense. The brain learned not just to communicate information, but to manipulate it, to wrap meaning inside meaning until words could hide intentions as easily as reveal them. The physical side of this adaptation can still be seen in our throats. The modern human larynx sits lower in the neck than in other primates, lengthening the vocal tract and enabling a greater range of resonant sounds. This came at a cost. It increased the risk of choking, a reminder that evolution never grants without taking. But the payoff was an instrument capable of fine modulation, vowels, consonants, rhythm. Combined with precise tongue and lip control, it produced an acoustic palate broad enough to carry complex syntax. Anatomical studies of the hyoid bone, which anchors the tongue and larynx, show that by about 100,000 years ago, humans already possessed the modern form. Speech, at least in potential, was ready. Still, potential is not performance. A brain with the machinery for language does not automatically use it. Neural circuits require practice and feedback to specialize. This suggests that spoken communication must have been common enough to shape development, even if its form was rudimentary at first. Imagine short proto-sentences combining gesture and sound, each generation adding layers of structure as children learn to predict and complete patterns. Over time, the brain itself began expecting grammar, pruning unused connections and reinforcing syntactic pathways. In a feedback loop spanning thousands of years, culture sculpted biology as much as biology enabled culture. The emergence of language also altered emotional life. Internal speech provides a mechanism for self-regulation, the ability to talk oneself through fear, anger, or confusion. Neuroimaging studies show that silent verbalization activates similar regions as audible speech, but recruits additional networks for self-monitoring. It is as though the brain learned to parent itself. The capacity for introspection, guilt, and deliberate calm may all trace back to this internal dialogue. In evolutionary terms, it was an advantage that turned impulse into consideration. Not all scientists agree on timing. Some argue that full syntactic language appeared much later, around 50,000 years ago, coinciding with behavioral modernity. Others propose that the neural groundwork was already in place 100 millennia earlier, maturing gradually. The truth may lie between. The hardware evolved early, the software refined over generations. What matters is that the foundation for symbolic thought and complex coordination was established. Whether whispered across fires or rehearsed silently in thought, grammar had begun its long tenure as the architecture of mind. Comparative studies with other primates illustrate the distance between communication and language. Chimpanzees can learn dozens of signs and even combine them, but their expressions lack recursion. They cannot say, "I think that you think that I want food." Their signals remain tied to immediate context. Even songbirds and whales, whose calls show remarkable structure, do not embed meaning hierarchically. Only humans create sentences that fold back on themselves, reflecting minds that can fold back too. That recursive mirror, language thinking about thought, became the core of consciousness. The neurological rewiring behind this achievement was subtle, but transformative. Connectivity between Broca's and Wernicke's areas strengthened. Subcortical loops through the basal ganglia and cerebellum refined timing and rhythm. Mirror neurons in the premotor cortex linked hearing and doing, allowing imitation of sounds. Each of these systems existed before, but in combination they crossed a threshold. The brain that once organized simple tool sequences could now organize concepts, nesting them in the syntax of speech. It is humbling to remember that we can only infer this revolution from bone and gene, not from preserved words. No fossil records the first metaphor, the first joke, the first whispered lie. We can only trace the scaffolding that made them possible. The earliest evidence of symbolic communication, beads, pigments, engravings, appears later, but the mind capable of producing them was being wired during these centuries. Language may have begun not as sound but as structure, a mental algorithm evolving invisibly until expression caught up. In the quiet timeline between 100,000 and 60,000 years ago, the human brain was rehearsing for a performance it did not yet give. The patterns of syntax and hierarchy that would one day build civilization were forming in neural silence. Thought itself was learning to speak. Perhaps that is why, even now, language feels inseparable from identity. To lose words is to lose coherence. To speak is to think aloud. Every sentence we form carries the faint trace of that ancient transition, when the first minds learned to converse with themselves. The grammar of thought, once a survival adaptation, became the rhythm of human existence. And somewhere in that long night of prehistory, a person sat by a fire, shaping sounds into order, discovering that the tongue could model reality, and that reality could be changed by how it was described. How does gossip shape a genome? By 80,000 years ago, human brains had reached their near-modern size and structure. The hardware was ready. What changed next was not anatomy, but the scale of social life. Small nomadic groups that once numbered a few dozen began merging, splitting, and reconnecting in patterns more complex than anything seen before in mammalian history. This expansion of interaction meant that survival no longer depended solely on knowing how to hunt or find shelter. It depended on understanding other people. Each mind became part of a network where trust, deception, reputation, and empathy determined who thrived and who vanished. The result was a new form of evolutionary pressure, one measured not in claws and teeth, but in relationships. The social brain hypothesis, proposed by anthropologist Robin Dunbar and others, suggests that intelligence itself expanded to keep track of social complexity. In primates, there is a correlation between neocortex size and average group size. Bigger groups demand more memory. Who groomed whom, who fought last week, who can be trusted to share food or watch a child. For humans, this requirement scaled up exponentially. A single misread alliance or forgotten betrayal could have life or death consequences. In such a world, mental acuity became survival. The brain, already an energy-intensive organ, evolved not merely to solve external problems, but to model the internal states of others. If we could step into one of those ancient camps, we might recognize the rhythm of conversation, the first quiet gossip sessions around the fire. Words allowed not just coordination of hunts or sharing of stories, but the creation of social order. Through speech, one could signal loyalty, share grievances, or test boundaries. Gossip sounds trivial, but in evolutionary terms it is governance. It enforces cooperation without violence by broadcasting information about behavior. The person who gossiped effectively could influence reputations, form alliances, and detect deceit. Over time, natural selection favored individuals with sharper social perception, better memory for relationships, and more nuanced emotional responses. Neuroscience gives this theory a biological backbone. The regions most involved in social cognition, the medial prefrontal cortex, temporoparietal junction, and superior temporal sulcus, are among the most expanded and metabolically active areas in the human brain. They underpin what psychologists call theory of mind, the ability to infer the beliefs, desires, and intentions of others. Once this circuitry became sophisticated enough, it enabled not just cooperation, but strategic empathy, the capacity to understand another's perspective while simultaneously pursuing one's own advantage. This is cooperation's paradoxical twin, manipulation, and both grew from the same soil. By 50,000 years ago, social life had become a balancing act between sincerity and strategy. Every gesture carried layers of interpretation. Generosity could be altruism or calculated investment. Anger could signal dominance or fear. The better an individual could read these layers, the more likely they were to navigate conflict and secure mates or allies. Anthropologists studying hunter-gatherer societies today find that influence often flows not from physical strength, but from reputation, the memory of fairness, storytelling skill, or humour. It is plausible that similar dynamics shaped early Homo sapiens. Those who could entertain, persuade, or mediate held disproportionate power, even without formal hierarchy. This subtle form of competition, cooperative yet competitive, drove what we might call the social brain arms race. Every increase in group size multiplied the number of relationships to manage. If one person interacts meaningfully with just 50 others, the number of potential pairwise relationships is over 1,000. Add in coalitions and overlapping families, and the combinatorial explosion becomes staggering. The only way to manage it was through ever greater cognitive efficiency. Memory evolved to tag emotions to individuals, allowing quick recall of who could be trusted. The hippocampus and amygdala, crucial for emotional learning, show particular development in humans compared with other primates. They form the database of personal history each of us carries unconsciously. Empathy, too, may have deep evolutionary roots in this period. Mirror neurons, cells that fire both when performing an action and when observing another perform it, enable imitation but also underpin emotional contagion. To feel another's pain or joy helps synchronize group behavior. But empathy without restraint can overwhelm. It must be paired with regulation, a function of the prefrontal cortex. The interplay between these systems created a dynamic balance, enough empathy to bond, enough distance to survive conflict. In that tension lies the psychology of humanity. The capacity for shared intentionality, the ability to pursue goals collectively, also transformed daily life. Coordinated hunting or gathering required anticipation of others' actions and trust that they would follow through. This dependence fostered moral emotions such as guilt and pride, neurological mechanisms that reinforce group cohesion. When one failed the group, shame activated the same neural circuits as physical pain, teaching the cost of social exclusion. We became wired to belong. Genetic evidence supports this emphasis on social selection. Certain alleles associated with neurotransmitters, dopamine, serotonin, and oxytocin pathways, show signs of positive selection in recent human evolution. Oxytocin, in particular, modulates trust and bonding. Variants that fine-tune its receptor sensitivity might have influenced how readily individuals formed attachments. These molecular adjustments mirror the behavioral ones, tiny chemical tweaks fostering the grand architecture of cooperation. It is easy to assume that natural selection favours selfishness, but in small interdependent communities, cooperation often outcompetes isolation. Those who shared meat or cared for others' offspring increased the survival of relatives and allies who later reciprocated. Over generations, kindness became strategy. At the same time, cheaters who exploited generosity without giving back were punished or ostracized. This feedback loop shaped both genes and norms, weaving morality into biology. Language amplified all of it. Even without discussing art or population growth, we can imagine how communication turned social pressure into an evolutionary engine. Words could build or destroy alliances faster than any physical weapon. Through speech, social selection became more precise. One could defend reputation, spread rumours, or apologise. The ability to use language persuasively became as vital as strength or dexterity. Those with verbal agility likely attracted allies and mates, embedding communication deep within the machinery of evolution. This period also forged the roots of emotional intelligence. Recognizing micro-expressions, tone, and posture offered clues to hidden feelings. The brain adapted to read these cues almost instantly. Today, dedicated neural circuits respond to facial emotion within milliseconds. Such speed mattered when trust determined access to resources or safety. A wrong inference could mean expulsion, or worse. The selective pressure for accurate social perception was relentless. We can see traces of this transformation in fossil faces. Compared with archaic humans, modern Homo sapiens have softer features, smaller brow ridges, reduced prognathism, and overall more gracile skulls. Some researchers suggest these changes reflect self-domestication, a process where reduced aggression and increased social tolerance were favoured. In other words, selection began rewarding the ability to coexist. The genes influencing neurochemical regulation of aggression may have been under the same pressure as those for intelligence. The result was a creature less likely to lash out and more likely to negotiate. To understand why this mattered, imagine the difference between a species that solves problems alone and one that does so collectively. Cooperation multiplies intelligence. 2 minds can exchange strategies. 10 minds can innovate solutions no individual could reach. Once humans learned to coordinate behavior across time and intention, cognition became distributed. Intelligence stopped being confined to one brain and began to exist between them. The tribe itself became a thinking organism. Of course, this new social landscape came with cost. Living among others means constant monitoring, evaluation, and emotional labour. The same brain that evolved to manage relationships also became vulnerable to social stress, ostracism, envy, status anxiety. Our capacity for self-awareness, born from modelling others' perceptions, also created insecurity. From an evolutionary perspective, such tension is the price of cooperation. The mind became both the weapon and the wound. By 50,000 years ago, these intertwined pressures, cooperation, competition, empathy, and deception, had moulded a species uniquely suited to social living. The human brain was no longer just a tool for surviving nature, but for surviving each other. The same networks that tracked alliances around campfires would one day build empires and political systems. The genetic legacy of gossip still runs through us, our need to share, to judge, to belong. We often imagine evolution as a march toward intelligence, but perhaps it was a drift toward intimacy. Minds sharpened not to dominate the world, but to understand the minds next to them. In that understanding, survival found a new form, not through claws or speed, but through connection. And so the story of the social brain is the story of us, creatures whose greatest strength lies not in isolation, but in the endlessly intricate dance of attention, emotion, and trust. Even now, every conversation, every whisper, every act of empathy continues the same quiet arms race that began 80,000 years ago, an experiment in collective survival that shows no sign of ending. When did ideas start breeding faster than people? Around 60,000 years ago, the human world began to hum with a new kind of energy. Populations were still small by modern standards, tens of thousands scattered across continents, but something invisible had crossed a threshold. It wasn't just that more people existed, it was that they were close enough, often enough for knowledge to accumulate rather than vanish. For the first time in evolutionary history, information had a memory larger than a single mind. Ideas could reproduce. For hundreds of thousands of years, human populations had been thinly spread, separated by deserts, mountains, and unpredictable climates. Each group carried its own fragile library of techniques: how to make a tool, where to find food, when to move with the seasons. But when numbers are low and generations short, innovation dies easily. A single death can erase a discovery. Archaeologists call this the cultural drift problem. Small, isolated groups lose complexity faster than they gain it. Survival favours reliability, not creativity. Yet as the climate stabilised in certain regions and networks of contact expanded, the arithmetic changed. Each additional person was no longer just another mouth to feed. They were another node in the web of shared memory. Genetic and archaeological models suggest that sometime after 60,000 years ago, the global human population began to grow steadily. This was not an explosion, more like a long, slow fuse. More people meant more interactions, more marriages across groups, more encounters between strangers. The old isolation broke down into a patchwork of connected bands. When populations reach a certain density, random meetings become predictable, and information can spread as reliably as genes. Innovation stops being an accident, it becomes inevitable. The logic behind this is simple but profound. Ideas, like organisms, need hosts. They mutate, compete, and adapt to the minds that carry them. A new tool or technique has a survival curve. If it spreads to enough individuals before being forgotten, it persists. The tipping point, the minimum number of carriers needed for an idea to outlive its inventors, is called cultural critical mass. Once humanity crossed that line, the rules of evolution changed. Biological adaptation slowed, cultural adaptation took over. We can glimpse this transformation in the traces of settlement. One of the most telling examples comes from Central Europe, at a place known as Dolní Věstonice, in what is now the Czech Republic. Excavations there reveal a scale of human gathering previously unseen. Dozens of hearths, bone structures, and tools cluster across several layers of sediment, spanning centuries of reoccupation. The number of hearths alone, more than 200, suggests a population of several hundred people at any given time, perhaps many more. Some researchers estimate that the broader network of nearby sites could have supported 10,000 individuals cycling through seasonally. For a species used to living in groups of 40 or 50, that was a metropolis. What mattered most about these concentrations wasn't their permanence, but their density. A camp that large turned knowledge into a public resource. Skills could specialise, one person mastering hide processing, another flint knapping, another navigating trade routes. When specialists exchange work, they also exchange insight. A successful innovation in one hut could ripple across the camp within days. The community itself became a brain, distributed, self-correcting, capable of remembering what no individual could hold alone. Evidence from sites across Africa, the Levant and Eurasia supports this picture. Around this period, we see an increase in standardized tools and regional styles. That consistency implies communication over wide areas. When populations are small, each group's technology drifts randomly. When populations interconnect, differences level out as the best ideas win. It's not the appearance of tools that marks the change, but their persistence. The fact that design traditions now lasted for thousands of years, copied and refined by people who might never meet the original inventors. Demography became destiny. Mathematic models of cultural evolution show that once a population reaches a certain threshold, likely in the tens of thousands, innovation rates accelerate exponentially. Each generation inherits a larger foundation to build on. Mistakes can be tested without catastrophic risk. Learning becomes more efficient because multiple examples exist. In short, humanity's collective intelligence acquired redundancy, the same principle that makes ecosystems stable and the internet resilient. If one node fails, others carry the signal. But this new abundance came with complexity. Living among hundreds or thousands required new levels of coordination and social negotiation. Food distribution, mating systems, and territory boundaries all demanded consensus mechanisms. The cognitive skills that had evolved for small group dynamics, empathy, memory, reputation management, now scaled upward. Leaders and mediators appeared, perhaps not in name but in function. Rules began to solidify into norms, customs into expectations. The foundation for political behaviour was being poured long before anyone imagined it as such. We don't yet know exactly where this tipping point first occurred. Africa's coastal refugees, with their rich marine resources, may have hosted early demographic blooms. The Nile Corridor, the Levantine Corridor, and parts of southern Asia all show overlapping timelines of expansion. The critical ingredient was not location, but connectivity. Wherever exchange networks formed through marriage, trade, or seasonal migration, innovation rates rose. The same logic that governs information spread in modern cities governed it then. Crowds don't just share ideas, they multiply them. Dolní Věstonice remains a striking window into that multiplication. Layers of mammoth bone huts and fire pits speak to organised labour and social memory. The repeated reuse of the site over generations suggests a kind of tradition, a sense that we belong here. Archaeologists have even found clay deposits bearing hundreds of impressions from woven mats or nets, evidence of domestic technology passed hand to hand. These are not the artefacts of isolated wanderers, but of a knowledge economy beginning to take shape. Why did it happen then, and not earlier? Part of the answer may lie in survival rates. As tool use, hunting strategies, and social cooperation improved, child mortality decreased slightly. Each small gain compounded across centuries. Populations could afford to grow denser without collapsing. Climate fluctuations also stabilized briefly after the worst chaos of the glacial cycles, allowing for more predictable migration routes and seasonal camps. Stability, paradoxically, created motion. People could return to the same places, and knowledge could accumulate. Genetic studies show that during this period, human lineages diversified regionally, but remained connected through migration. This maintained genetic health and allowed ideas to travel alongside people. The same migration corridors that moved genes moved memes, the mental equivalents of genes spreading innovation through imitation. Each migration wave carried new techniques, which either blended or replaced older ones depending on efficiency. Evolution was no longer about who survived the environment, but whose information survived transmission. We tend to picture the deep past as static, but for the people living it, life was accelerating. Children grew up in larger communities, exposed to more voices, more tools, more habits. Learning itself evolved. The neural plasticity of the human brain, already remarkable, became an advantage in an environment where cultural knowledge updated faster than genetic change. This is the point where education, in its earliest sense, was born. Not classrooms, but observation and imitation within dense social webs. The species had invented something more powerful than language or fire: cumulative learning. From this moment onward, every new generation began a few steps ahead of the last. The curve of knowledge bent upward. What we see in the fossil and archaeological record is not sudden genius, but slow inevitability. When enough minds connect, intelligence stops being individual. It becomes a property of the network. Humanity had reached critical mass. If there is a lesson in this ancient threshold, it is that progress rarely comes from isolation. The same density that sparked innovation also required tolerance. Crowded camps forced cooperation and patience. People learned to coexist not out of virtue, but necessity. The rewards were immense: resilience, creativity, adaptability. But it also set the stage for everything to come: competition, hierarchy, and the restless momentum that would carry our species across the planet. We can only reconstruct fragments of that shift: hearths, bones, footprints, the charred remains of shared meals. Yet behind those traces lies a mathematical truth that still governs civilization. Once information began to outpace reproduction, humanity entered a new evolutionary regime. The body stayed the same, but the collective mind began to accelerate. The species had invented a way to evolve without waiting for mutation, and that, perhaps, is when ideas started breeding faster than people. Why did imagination suddenly leave fossils? Around 45,000 years ago, the archaeological record changed from silence to symphony. For hundreds of millennia, humans had left behind only tools and bones, the unremarkable residues of survival. Then, almost everywhere at once, the world began filling with images, ornaments, figurines, and sound. Caves lit by flickering torches bore painted walls of bison and horses. Carved ivory animals appeared in the river valleys. Hollowed bird bones turned into flutes. For the first time, human thought became visible and audible. Archaeologists call it the Aurignacian, a period when imagination materialized as evidence. At first glance, the suddenness of this transformation seems supernatural, but it was not magic. It was momentum. For tens of thousands of years before, the building blocks had been accumulating: language, cooperation, population density, and memory. When those systems reached a certain threshold, culture began evolving like a living organism, subject to variation, inheritance, and selection. The Aurignacian explosion was not a beginning, but a bloom, the visible flowering of roots already deep in time. The earliest signs of this outburst appear across Europe between 45 and 35,000 years ago, though the process likely began earlier in Africa. One of the most striking discoveries comes from the Swabian Jura in southern Germany, where caves like Vogelherde, Hohlefels, and Gießenklosterle have yielded miniature masterpieces carved from mammoth ivory. Among them is the Lion Man of Hohensteinstadel, a figure combining the body of a human with the head of a cave lion. Standing about 30 centimeters tall, it is the oldest known figurative sculpture on Earth. Its creator had to imagine something that did not exist, to combine real forms into a symbolic one. That single act marks a threshold, the invention of myth. Nearby in Hohlefels, archaeologists uncovered delicate flutes made from vulture bones and mammoth ivory. The oldest, dated to roughly 40,000 years ago, still plays a clear tone. Through these instruments we glimpse the birth of organized sound, the moment when rhythm and melody became more than instinct. Music is cooperative memory. It coordinates emotion across groups. In a world of uncertainty, shared songs would have been more than art. They were cohesion. The same caves reveal beads, pendants, and ornaments drilled with precision. Some were made of ivory, others from the teeth of foxes or wolves, suggesting symbolic use beyond utility. Ornamentation transforms the body into message: who one is, to whom one belongs, what one values. In these small objects lies the earliest record of identity constructed through culture rather than biology. Further south, in France and Spain, the walls of limestone caverns turned into living canvases. At Chauvet, paintings over 36,000 years old depict lions, rhinoceroses, horses, and mammoths in motion. Lines curved and overlapped to suggest movement. The artists used shading, perspective, even flickering torchlight to animate the figures. In Lascaux and Altamira, generations later, the same tradition matured into vast sanctuaries of colour and form. These are not random doodles. They are deliberate compositions, layered over centuries, sometimes revisited long after their creators were gone. Each stroke implies teaching, imitation, and tradition, a visual lineage. Why here, and why then? Archaeologists debate, but the consensus points to cumulative culture reaching critical density. As populations grew and groups interacted more frequently, innovations no longer vanished with their inventors. One generation's experiment became the next's foundation. A method for grinding pigment, a technique for shaping ivory, a pattern of dots representing animals, all of it persisted. Creativity, once fragile, became self-sustaining. Ideas began reproducing faster than genes. This creative cascade wasn't confined to Europe. In Africa, at sites like Blombos Cave and Apollo 11 in Namibia, engraved ochres and painted stone show similar patterns of symbolic behaviour, predating the Orogenation by tens of millennia. What changed later was scale and continuity. The record becomes dense enough that we can trace the diffusion of motifs and techniques across thousands of kilometres. A visual language was spreading, evolving regionally yet recognisable globally. The first hints of a shared human aesthetic. This period also shows an increase in specialised tools for specific tasks: scrapers, burins, points, and awls. Such differentiation implies planning and foresight. Instead of one all-purpose implement, people created toolkits optimised for different materials: bone, wood, hide. Each required recognising that form follows function, an engineering principle millennia before the word existed. The human mind was no longer adapting only to nature but redesigning it in miniature. One of the subtler consequences of this transition is the emergence of what psychologists call affordance recognition, the ability to see potential uses in an object before acting. A stone core offered not just one possible tool, but a dozen latent within it. The brain learned to perceive possibility embedded in matter. This shift from reactive to generative perception marked another step toward modern cognition. Tools were no longer passive, they became active partners in thinking. Standardization also enabled collaboration on a new scale. Once designs were predictable, multiple people could contribute to the same production process. One shaping cores, another detaching blades, another hafting them into handles. Knowledge became modular, like the tools themselves. This division of labour may have been one of the earliest forms of technological specialisation, turning craftsmanship into a communal enterprise. We can see echoes of this cognitive expansion in how toolmakers began to plan for mobility. Blade cores were often shaped at quarry sites and carried long distances before being reduced elsewhere. That means the maker was anticipating future needs, abstract time projected into material form. A core was both object and promise, a portable reservoir of potential tools. In this sense, technology became time travel, allowing a person to prepare for situations not yet encountered. It's tempting to think of these innovations as inevitable progress, but evolution has no script. The blade industries required not only intelligence but social stability, enough continuity for skills to be transmitted accurately. Teaching napping takes patience, observation, and feedback, the same ingredients as pedagogy today. A single generation of disruption could have erased the knowledge. That it persisted tells us something about the resilience of these early communities. They had created not just technology, but institutions of learning, even if those institutions were nothing more than the repetition of gestures by firelight. Some researchers argue that these technologies represent the earliest examples of cumulative technological evolution, a process where designs build upon one another, retaining earlier improvements. Each new variant of blade or point subtly refines the geometry, efficiency, or hafting method of its predecessor. Over centuries, this created a self-sustaining technological lineage. The artifacts of the Upper Paleolithic are not static relics, they are snapshots of an evolving system of cognition and craft. When viewed this way, the question, can a stone hold a memory, becomes literal. Every flint fragment preserves the thought patterns of its maker, angles, pressures, sequences. Modern experimental archaeologists can reconstruct those gestures, revealing remarkable consistency across vast distances. The same methods appear from the Atlantic coast to Siberia, suggesting long-range transmission networks that predate agriculture by tens of millennia. The Stone Age, in this sense, was also the age of information. Perhaps the most fascinating aspect of these industries is their feedback effect on cognition itself. Handling tools reorganizes the brain. Studies of modern knappers show that the process activates networks associated with language and motor planning. The rhythm of striking stone engages areas of the left hemisphere similar to those used in speech. This overlap may not be coincidence. The physical discipline of toolmaking could have reinforced neural pathways that later supported syntax and sequencing. If so, technology did not just mirror thought, it sculpted it. By 30,000 years ago, the system had matured. Blade technologies diversified into regional traditions, Gravettian, Solutrean, Magdalenian, each refining the concept of precision manufacturing. The innovation curve slowed not because creativity faded, but because the available materials had been mastered. What changed instead was scale. Tools became social currency, exchanged across vast distances, each piece carrying the logic of its design into new lands. The network of memory had become global. In these stones lies the quiet proof that intelligence can live outside the skull. The tools of the late Pleistocene were not merely implements of survival, but repositories of thought. They allowed knowledge to persist independently of the individuals who discovered it, creating a bridge between minds across generations. The first libraries were not written, they were napped. And perhaps that is why the archaeology of this period still feels alive. Each flake, each scar, each worn edge is a sentence in a conversation that never ended. The tools remember not in words, but in form. The rhythm of innovation that began when our ancestors realized that the world could be shaped to think with them. Can a stone hold a memory? Between 45,000 and 30,000 years ago, humans began shaping matter as if it could think alongside them. The shift from the old Mousterian flake tools to the new, slender blades of the Upper Paleolithic was not just a technical improvement, it was a change in how knowledge itself was stored. A stone could now contain instructions, a tool could teach. For hundreds of millennia, stone technology had followed a patient, predictable rhythm. Neanderthals and early Homo sapiens mastered the Levallois technique, striking a prepared flint core to produce one precise flake. Each piece was the result of individual craftsmanship, but it was also ephemeral. Once used, it vanished into history. The skill lived only in the knapper's hands and died when they did. The stone recorded no method, only the outcome. Around 45,000 years ago, the geometry of toolmaking changed. Instead of removing single flakes, humans began preparing long cores that could yield a series of near-identical blades, thin, symmetrical, and standardized. This innovation multiplied output and precision, but more importantly, it transferred part of the learning process into the object itself. The core became a kind of fossilized plan. Its contours preserved the logic of the maker's strikes, allowing others to reproduce the sequence by reading the scars on its surface. The stone had become a medium of memory. Archaeologists see this transition across Europe, the Near East, and Siberia. The evidence is consistent. More elongated blades, higher edge-to-mass ratios, and increasingly modular tools designed for hafting, attaching to handles or spears. It was as if toolmakers were no longer sculpting individual solutions, but building a system of interchangeable parts. Once learned, the method could be applied to any raw material, any landscape. A cognitive shift was underway. The idea of replication had entered technology. At sites like Sarakil in Lebanon, Kostenki on the Russian plains, and Abri-Castanet in France, the same recurring forms appear. Brins for engraving, scrapers for hides, points for piercing. Each shows careful standardization. The similarity across vast distances suggests shared templates, passed through generations not by memory alone but by demonstration and artifact. A well-shaped core taught its student more effectively than words could. The rhythm of percussion, the angles of removal, the symmetry of the blade, all these were instructions written in stone. What separates a flake from a blade is not sharpness but foresight. To strike a Levallois flake, one thinks in single actions. To shape a blade core, one must plan an entire sequence of removals, envisioning the pattern before it exists. Archaeologists call this hierarchical organization actions nested within actions, decisions layered through time. It is a way of thinking we take for granted now, but at that moment it was revolutionary. The toolmaker was not reacting to stone, they were conversing with it, anticipating its fractures as a musician anticipates notes. Experimental archaeologists who replicate these tools describe the process as dialogue. A good core responds predictably, its geometry guiding the next move. In that sense, the technology itself participates in teaching. Cognitive scientists refer to this as externalized cognition, the idea that tools don't just extend our bodies, they extend our minds. Each hammer blow is both an act of shaping and of remembering. The knowledge encoded in the artifact feeds back into the brain that uses it, reinforcing skill through repetition. This feedback loop may have been humanity's first form of mechanical learning. Once a community adopted a standardized method, it no longer had to reinvent every detail. The process became collective. A single skilled napper could train others simply by leaving behind good cores. The next generation, analyzing the old scars, could reverse engineer the thinking behind them. Knowledge no longer depended entirely on memory or oral explanation. It was stored in matter waiting to be reactivated by touch. At this point, the human toolkit diversified dramatically. The repertoire expanded to include awls, burins, and bladelets, each adapted for specialized tasks, scraping hides, carving bone, or shaping wood. What ties them together is consistency. Unlike earlier tools, which varied wildly in size and form, these new implements obeyed geometry, parallel edges, uniform thickness, standardized angles, all signs of abstract design principles. The maker no longer thought of a single tool, but of a type. That mental abstraction is what separates a craft from an invention. One of the subtler consequences of this shift is the emergence of predictive reasoning in material culture. A good blade core could yield 10 or 20 usable blades, meaning its creator was projecting utility into the future. The act of toolmaking became an act of time travel, anticipating needs, conserving resources, and planning for work not yet done. In that sense, every core was both a tool and a plan for future tools, a durable record of foresight. The archaeological record also reveals a new sensitivity to material properties. Toolmakers selected specific flints or cherts with fine-grained texture, learning how to heat-treat them for easier shaping. This required controlled fire use and empirical testing, a fusion of physics and patience. The result was a precision industry running without machines, where every detail was discovered through experiment and retained through replication. As blades spread across continents, their uniformity suggests that learning had become portable. A single napper could travel hundreds of kilometers and immediately recognize the work of others. The design spoke a universal language of efficiency. Technology had achieved something language alone could not. It standardized thought. In a sense, humans had begun outsourcing part of their cognition into the objects they created. The world was becoming a distributed memory system. Even the act of teaching itself was evolving. Toolmaking requires mirroring gestures, reading intentions, and adjusting rhythm, skills that strengthen the same neural circuits used for imitation and empathy. When one person taught another to nap, both engaged in a synchronized dance of perception and movement. This social dimension of craft likely reinforced cooperation, patience, and shared identity. The stone became not only a record of technique but a medium of connection. We can see this process of cumulative refinement clearly in the progression from Aurignacian to Gravettian tool industries. Each phase shows incremental improvements, blades becoming thinner, retouching more controlled, cores more efficiently prepared. No single discovery defines the shift. Instead, it is the steady optimization of systems. The tools evolve faster than biology ever could, guided by learning loops that no longer relied on genetic inheritance. Culture had achieved its own version of evolution, with selection acting on ideas instead of DNA. This idea, that a stone could store intention, remains one of archaeology's most profound insights. A flint core is not a fossil of technology alone, it is a fossil of thought. Its surfaces preserve the sequence of mental operations that produced it, frozen mid-process. When modern researchers refit the flakes back onto a core, they can reconstruct the maker's reasoning blow by blow. Each scar is a neuron's echo, each curve a record of ancient decision-making. In that sense, yes, a stone can hold a memory, not of images or words, but of procedures, rhythms, and relationships between force and form. It remembers through pattern, just as the brain does, and as those patterns pass from hand to hand, they shape the species that made them. The human mind did not merely invent tools. Tools helped invent the human mind. How do you survive a world that wants you gone? Between 30,000 and 20,000 years ago, Earth locked itself into its coldest phase in over 100 millennia. Ice sheets 2 kilometers thick pressed down across the northern continents. The great European plains turned to tundra, windswept and barren. Average temperatures plunged. The oceans withdrew into frozen reservoirs, lowering sea levels by more than 100 meters. To most mammals, this was extinction weather. But humans did not just endure the last glacial maximum, they outthought it. This was not a triumph of warmth, but of planning. When resources thinned and the horizon turned white, people began engineering their way through the freeze. The archaeological record from this period, spanning roughly from modern France to Siberia, reads like a manual of ingenuity under pressure. Every adaptation, from clothing to shelter to hunting coordination, tells the same story. Intelligence became insulation. Let's start with the simple fact that the human body was not designed for this climate. Our species evolved in Africa, in sunlight and savanna heat. We lack dense body hair, thick subcutaneous fat, or claws to dig through ice. Yet by 30,000 years ago, our ancestors were thriving in conditions colder than modern Greenland. The trick was technology turned inward, the invention of the artificial skin. Bone needles, some smaller than matchsticks, appear across sites from the Czech Republic to Russia during this era. They are finely pierced, sometimes even grooved, designed for threaded stitching. With them came tailored clothing, not draped hides, but fitted garments. Archaeological residues of fur species suggest layered systems, reindeer or a fox for insulation, mammoth hide for outer shells, and sinew or plant fibres twisted into cord. People were no longer wrapping themselves in nature, they were designing their own microclimates. The clothes they wore were not luxury, they were thought made visible. Shelters followed the same logic. At Dolní Věstonice in Moravia, massive dwellings built from mammoth bones stand as frozen blueprints of survival engineering. Circular frames of tusks supported thick hide coverings, with hearths at the centre and storage pits along the edges. The bones were not just structural, they acted as thermal mass, holding and slowly releasing heat. Outside, winds could reach hurricane strength. Inside, temperatures might have stayed above freezing, a triumph of cooperation and geometry. In these icy villages, knowledge had become architecture. Even mobility was redesigned. Hunters of the Eurasian plains developed composite weapons, spears and atlatls or spear throwers that multiplied force without adding weight. A curved lever extended the hunter's arm, allowing a projectile to fly farther and hit harder. The principle is simple physics. but its execution required understanding elasticity, trajectory, and timing. When every hunt meant survival, a well-thrown spear became a mathematical problem solved in real time. Food was another puzzle. During the glacial peak, herds of mammoth, horse, and bison roamed the steppes, but their migrations were unpredictable. People learned to track not just animals, but seasons and ice itself, the direction of winds, the growth of lichen, the cracking of frozen rivers. Archaeologists studying faunal remains find evidence of strategic culling, groups taking juveniles in summer, adults in winter, maintaining herds at sustainable levels. It was proto-ecology, not by philosophy, but necessity. And yet, perhaps the most remarkable adaptation was social, not technological. In a world of scarcity, survival meant cooperation. The scale of coordination visible in glacial period sites is astonishing. Dolnivestonis again offers clues. Evidence of thousands of hearths across several layers suggests a settlement large enough to house 10,000 people seasonally. That required resource pooling, task specialization, and communication networks capable of moving information as efficiently as food. In the Ice Age, civilization's skeleton was already forming under the snow. Among the many survival partners humans found during this period, one stands out. Not fully tamed, not yet dog, but no longer purely wolf. Around 23,000 years ago, genetic evidence suggests a small population of wolves began living in proximity to humans, likely scavenging from camps. Over time, they adapted to our presence, responding to vocal cues, alerting camps to predators, and sharing in hunts. In return, they received warmth and food. Whether the partnership began through accident or intent, it became symbiotic. The Ice Age forged a contract. Intelligence recognizes intelligence. The first companions of humanity were not tools, but minds on four legs. Fire, the oldest ally, also reached new sophistication during this era. Hearths became central fixtures of daily life, often arranged in clusters within shelters. Ash layers show repeated cleaning and reuse, meaning fire was now routine, not an event. Charcoal residues reveal selective burning, certain woods preferred for longer heat, others for smoke control. Some sites even hinted open-air kilns for hardening clay figurines or treating flint. The mastery of fire had turned into thermal science. To survive in the Ice Age also meant mastering light. During the long winters, sunlight could vanish for months. People made lamps from hollowed stone or bone, filled them with animal fat, and burned twisted plant fibres as wicks. In these small flames, the night retreated. Light became portable, extending waking hours for toolmaking, storytelling, and teaching. It may be here that human culture first learned to glow in the dark. The fossils of those who lived through the last glacial maximum tell the same story their tools do. Resilience carved into bone. Their skeletons were strong, adapted to hard labour, yet their teeth show signs of cooked diets and processed grains, hints of culinary experimentation even in frozen lands. These were not desperate survivors, but adaptive thinkers. They engineered comfort where none should have existed. It's easy to imagine the Ice Age as silent desolation, but that silence was full of invention. Every layer of adaptation, from the warmth of stitched furs to the architecture of mammoth dwellings, was an act of imagination under duress. Each problem forced the mind to stretch a little further, to hold the world in models and predictions rather than mere reactions. By the time the ice began to melt around 20,000 years ago, Homo sapiens had become an animal that could redesign its entire environment to fit a plan. The ice did not just test intelligence, it refined it. It stripped away complacency, rewarding foresight and punishing neglect. Those who survived were not necessarily the strongest, but the most observant, the best collaborators, the ones who could see pattern in chaos. In this frozen crucible, the human brain became what it is today. Not a weapon, but a climate control device. Thought, at last, had learned to keep itself warm. What happens when ideas evolve faster than genes? Somewhere between 40,000 and 20,000 years ago, human evolution changed its tempo. The body stayed the same, but the mind began to move at a speed that biology could no longer match. Adaptation no longer came from mutation or natural selection, it came from teaching. A new form of inheritance emerged, one carried not in DNA, but in memory, imitation, and storytelling. It was the birth of cultural evolution, and from that moment survival would depend as much on communication as on biology. For millions of years before this shift, the story of evolution was written in flesh and bone. A longer femur meant faster running, a stronger jaw meant better chewing. But these changes took tens or hundreds of thousands of years to appear. Then, suddenly, Homo sapiens began changing in ways no skeleton could record. Within a few thousand years, the blink of an evolutionary eye, we see new tools, new shelters, new art, new ways of thinking. The pace of innovation became so rapid that it could no longer be explained by genetic drift or selection pressure alone. Something else had begun rewriting the rules. To understand what changed, it helps to think of an idea as a kind of organism. Like a gene, an idea can replicate, mutate, and compete for survival, not in the body, but in the mind. When one person discovers a technique and another imitates it, that idea reproduces. When someone improves it, the new version outcompetes the old. Over generations, useful or beautiful ideas spread, while the clumsy or inefficient ones vanish. This invisible ecosystem of knowledge, tools, behaviours, myths, techniques, began evolving inside the species itself. It was a new Darwinian world, one made of thought. Archaeologists can see this process in the layers of sediment that mark the Upper Paleolithic. Each layer represents not a different kind of human, but a different version of humanity's collective mind. At 40,000 years ago, we find the first standardized blade industries. By 30,000, complex weapon systems. By 20,000, tailored clothing, kilns, and architecture. None of these required new genes, only new minds sharing information faster and more efficiently. Imitation was the first bridge. Humans have always been exceptional mimics. Children learn by watching, adults refine by observing. Neuroscientists today call this mirror learning. When watching someone perform an action activates the same neural pathways as doing it yourself. Our ancestors didn't need classrooms, they needed proximity. Around a fire, knowledge flowed as easily as smoke, carried by gesture and rhythm. A glance at another's hands could reveal a secret of toolmaking or firecraft. For the first time, learning became exponential, one mind improving the next across generations. Teaching too evolved. Unlike imitation, teaching requires recognizing ignorance in another and adjusting behavior to fix it. It's a recursive act. To teach, you must know that someone doesn't know. Archaeologists have found little direct evidence of teaching, but its traces lie in the increasing complexity of technologies that could not be mastered by imitation alone. The fine bone needles, the multi-step heat treatment of flint, the preparation of pigments, these skills require explanation, not just observation. When teaching emerged, evolution gained an accelerator pedal. Once information could be transmitted deliberately, the next step was refinement. Cultural memory began to accumulate corrections, knowledge no longer reset with every death. Mistakes were remembered, not repeated. With this came specialization. Some individuals focused on stonework, others on hunting strategy, others on navigating the seasons or reading animal tracks. No single brain held the entire survival manual anymore, but collectively the group did. The tribe became an extended intelligence, a living archive of skill. This system had one enormous advantage over biological evolution. It could adapt in real time. When climate shifted or prey disappeared, humans did not have to wait for random mutations to save them. They could experiment, learn, and transmit success within a single generation. A good idea could spread faster than any gene ever could. In that sense, the species had invented a second form of inheritance. Biological evolution shapes the body. Cultural evolution shapes behaviour. Together, they became inseparable. Some researchers call this the ratchet effect. Once a useful idea is discovered, it locks in, and future generations build on it rather than starting over. The cumulative result is visible in every artifact from this era. Blades that improve in symmetry, dwellings that evolve in layout, clothing that becomes more efficient with each version. The ratchet only turns forward because humans remember. Forgetting became the only true extinction. Language amplified this process. Though it likely began earlier, by 40,000 years ago, it had become sophisticated enough to convey abstract instruction. Words could now describe steps in a process, rules and conditions, the grammar of problem-solving. A concept could be transmitted across space and time, no longer dependent on demonstration. If genes are the memory of the body, language became the memory of the species. There is humility in realizing how fragile this system is. Ideas depend on hosts, and hosts die. Every generation had to reforge the link between knowledge and survival. When population densities dropped, traditions could vanish overnight. A forgotten knot, a misremembered recipe, an extinct technique. Archaeologists sometimes find abrupt gaps in cultural continuity, moments when entire technologies disappear for centuries. Evolution, even cultural evolution, is not a ladder but a web, threads breaking and reweaving as time moves on. By 20,000 years ago, this web had thickened. Knowledge was moving not just between individuals but between groups. Trade networks stretched across hundreds of kilometres. Shells from the Mediterranean appear in Central Europe. Pigments from distant quarries show up in Siberia. These exchanges carried not just goods, but ideas: how to hunt, how to build, how to make light in darkness. Innovation no longer belonged to one lineage. It belonged to the species. If we could condense this period into a single sentence, it might be this: humanity learned to evolve without mutation. Survival became a matter of imagination, of keeping pace with the ideas that shaped the environment. Culture, for all its complexity, is simply evolution sped up by memory. And perhaps that is why, even now, our species never stops changing. Once the brain discovered that information could replicate faster than genes, it never looked back. Biological evolution gave us the capacity for culture, and culture in turn began rewriting evolution itself. Were we already programming before computers? Between 20,000 and 10,000 years ago, something extraordinary began happening inside the human brain. For nearly 2 million years, evolution had shaped the species through slow genetic change. Broader skulls, finer hands, faster neurons. But in this narrow window, Homo sapiens began doing something new, altering its own cognitive environment faster than biology could keep up. Information no longer came from instinct or inheritance. It came from external systems, marks, tools, and symbols that expanded what the brain could do without physically changing it. We had begun, in essence, updating ourselves. By 20,000 years ago, human culture had become so information-rich that memory alone was no longer enough. A single community might have hundreds of tool types, dozens of plant processing techniques, maps of hunting territories, and complex oral genealogies. Every generation was born into a larger archive of knowledge than the last. At some point, the brain had to start outsourcing. The first data storage systems appeared, not in clay tablets or servers, but in bone and stone. Among the earliest of these cognitive artifacts is the Ashango bone, discovered near the headwaters of the Nile. Carved roughly 20,000 years ago, it carries rows of incised notches arranged in deliberate groupings. The spacing is too regular to be decoration. It suggests arithmetic. Some researchers believe the notches represent a lunar calendar, the tracking of days or moon phases, while others see simple tallies, the beginnings of numerical abstraction. Whatever the purpose, the act itself is revolutionary. Information captured outside the mind, encoded for retrieval later. Other examples appear across continents. Tally sticks from Europe, ochre-marked bones from South Africa, engraved stones from the Levant. They all share one principle: representation. A mark stands for something absent. The mind had learned to detach meaning from immediate experience and to manipulate symbols that refer to invisible things. Quantity, time, obligation. Once thought could be stored in matter, memory gained permanence. The nervous system had found an external hard drive. This new relationship between mind and object began to reshape the brain itself. Archaeologists and neuroscientists studying the period note an increase in tool diversity and complexity, corresponding with expanded neural integration across different cognitive domains. motor control, language, spatial reasoning, and working memory. Each domain had once evolved for separate survival tasks, but now they were being cross-wired through symbolic activity. Engraving a tally line, for instance, links vision, motion, and numerical reasoning in a single act. The brain became more plastic, less specialized, an organ capable of rewiring itself to handle whatever the mind invented next. Symbolic notation was only part of this new mental ecology. The spread of long-distance trade, which by this period connected regions thousands of kilometers apart, introduced another kind of computation, logistics. Managing who owed what, when, and how much required a new cognitive skill, tracking invisible networks of exchange. Oral tradition could preserve some of it, but not all. The invention of physical record-keeping, stones arranged in patterns, carved bones marking obligations, was a response to cognitive overload. The more humans thought, the more tools they needed to manage their own thinking. This self-reinforcing cycle, technology creating the need for better cognition, and better cognition creating more technology, became the defining loop of Homo sapiens. The shift is visible even in the organization of living spaces. Late Ice Age dwellings, from Mazin in Ukraine to Pinsevent in France, show evidence of spatial zoning, areas for tool production, hide processing, food preparation, and symbolic activity. These weren't just shelters. They were structured environments, externalized models of the mind's own organization. Humans were beginning to think architecturally, both in physical space and in conceptual space. What's striking is how cooperative this process was. Every innovation, from counting marks to cooking strategies, depended on imitation and shared correction. No single brain could have discovered cumulative knowledge on this scale. It required a distributed network of learners constantly refining, transmitting, and archiving information. When neuroscientists today describe the social brain, this is what they mean. Cognition not as an individual trait, but as an emergent property of communication. A lone genius carving tally marks is impressive. A group collectively maintaining systems of notation for generations is civilization in embryo. The neurological cost of this intelligence boom may have been significant. As cognitive demands rose, brains had to manage unprecedented information loads, not just remembering, but remembering how to remember. Archaeological endocranial evidence shows subtle changes in frontal lobe morphology over the last 30,000 years, possibly reflecting increased working memory and attention control. But perhaps more telling than anatomy are the behaviors themselves. Ritualized learning, symbolic play, the universal use of tools as extensions of the nervous system. These patterns suggest a flexible, plastic brain constantly adapting to its own inventions. In a sense, this was humanity's first technological singularity, not powered by machines, but by teaching. The moment knowledge began to accumulate faster than it could be genetically encoded, humans stepped off the track of biological evolution and onto a self-made path. Each new generation started slightly ahead of the last, inheriting not just genes, but instructions for thinking. Cultural evolution had matured into cognitive engineering. The symbolic artifacts of this period, the tally bones, engraved stones, and counting marks, seem modest, even primitive. But they represent the same leap in abstraction that led to modern computation. Every line or notch is a rule applied to data. Every pattern implies an algorithm. When you scratch parallel lines into a bone to represent days, you've created a one-dimensional database. When you add spacing or grouping, you've invented structure. Without realizing it, the species was learning to program, not machines, but reality itself. By 10,000 years ago, the consequences were clear. Human societies could now store, transmit, and refine more knowledge than any individual could hold. The species had effectively externalized intelligence, scattering fragments of mind into its artifacts. The world itself had become part of human cognition. Stone, bone, and pigment were no longer passive materials. They were co-processors, extensions of thought. This transformation did not end with the Ice Age. Once the brain discovered it could augment itself through symbols, it never stopped. Every future leap, writing, mathematics, science, even digital code, would follow the same principle first tested on those ancient tally marks. Information stored outside the skull, yet deeply inside the species. Evolution had not stopped. It had simply changed medium. Can kindness be an evolutionary weapon? Somewhere between 50,000 and 15,000 years ago, human survival began depending less on sharpness of tooth and more on the subtle wiring of empathy. Cooperation was not just a social nicety, it was a biological advantage. The Ice Age was ruthless, unpredictable and vast, yet scattered bands of Homo sapiens endured by forming networks of trust stronger than any predator's muscle. It is here that natural selection began rewarding generosity, fairness and even punishment, shaping the emotional circuitry that still governs human societies today. For most of life's history, competition ruled. Evolution rewarded the fast, the strong and the selfishly efficient. But humans were different. Alone, each individual was fragile, slow, hairless and poorly armed. Together they became formidable. Cooperation in this sense was not moral progress but evolutionary math. Groups that shared information, pooled food and defended one another had higher survival rates than those that fractured under stress. The evidence for this shift lies both in fossils and in the molecular traces still flickering in our genomes. By 50,000 years ago, the human brain was already anatomically modern, but it was still learning to manage the emotional complexity of group life. The expansion of the prefrontal cortex, which had begun long before, now reached its full behavioural potential. This region is not only the seat of planning and inhibition, it is also the control room for empathy. It allows one mind to model another, to anticipate reactions and adjust accordingly. Anthropologists call this theory of mind, the ability to imagine what others feel and think. It is an invisible skill, but its fingerprints can be seen in how early humans lived, how they shared, buried, and even punished. The archaeological record hints at this shift. Around 40,000 years ago, burial sites begin to show signs of deliberate care. Bodies positioned gently, adorned with red ochre or beads, sometimes accompanied by tools. These were not acts of utility, they were acts of recognition, the understanding that another's life held meaning even in death. The same cognitive empathy that made mourning possible also made cooperation predictable. When you can feel what others feel, betrayal becomes harder, loyalty more rewarding. But empathy alone could not stabilize large groups. Compassion needed structure. Evolution found it in neurochemistry. Deep within the hypothalamus, a small peptide called oxytocin became the silent engineer of trust. In modern humans, oxytocin is released during touch, eye contact, and cooperation. It lowers fear, strengthens memory of social bonds, and increases generosity toward familiar faces. Genetic studies of the OXTR gene, which codes for oxytocin receptors, show that certain variants associated with empathy and prosocial behavior have been under selection since at least the late Pleistocene. In other words, nature began experimenting with friendliness as a survival strategy. Yet cooperation comes with a paradox. To trust others, you must be vulnerable, and vulnerability can be exploited. This created a new kind of evolutionary arms race, not between predator and prey, but between altruism and deceit. Groups that could detect cheaters, punish freeloaders, and reward honesty outcompeted those that could not. Behavioral ecologists call this the problem of cooperation, and prehistoric humans solved it, not through conscious design, but through cultural selection. Norms evolved, unwritten rules enforced by emotion. Shame, pride, guilt, and outrage became the guardians of social order long before law or religion. Archaeological and ethnographic parallels support this. In hunter-gatherer groups, sharing meat after a successful hunt was both expected and monitored. Those who took more than their share risked exclusion from future hunts, or worse, social isolation, a death sentence in the Ice Age. Even mild punishment such as ridicule or gossip was enough to enforce fairness. This emotional policing required no leader. The group itself became the enforcer, each member wired to detect inequality. Cooperation was not just encouraged, it was defended. Over generations, this behavioral ecosystem likely sculpted our genomes further. Genes linked to serotonin regulation, stress response, and reward systems show signs of balancing selection, meaning that both empathy and caution were maintained in delicate equilibrium. Too much trust made one exploitable, too little made one isolated. Evolution fine-tuned the chemistry of belonging, Somewhere within this balance, humans began to experience cooperation not as obligation but as pleasure. Neuroimaging studies of modern humans show that acts of generosity activate the same reward centers as food and sex. It is possible that this rewiring began deep in the Pleistocene, when cooperation meant survival, and the brain learned to treat connection as nourishment. Each shared meal, each helping hand around a fire, reinforced neural loops of satisfaction. The kindness that feels natural today may be the echo of selection pressures carved by glacial winds. The size of social groups also expanded dramatically in this period. Earlier hominins lived in small family units, rarely exceeding 50 individuals. By 30,000 years ago, evidence from settlement sites like Dolny Vestonis and Kostenki suggests coordinated gatherings of hundreds or even thousands during seasonal hunts and migrations. Managing that many relationships required new social software: gossip, symbolic identity, reputation. Language, already sophisticated by then, became a technology of trust. With it, people could monitor the unseen: who helped, who lied, who could be relied upon. Information itself became a social currency, and the most successful individuals were those who could navigate it. This rise in collective complexity likely exerted strong selection on emotional intelligence, the capacity to regulate one's own feelings in order to cooperate effectively. In a world of perpetual stress, patience and forgiveness could be as life-saving as speed or strength. Even aggression found new purpose. Controlled anger enforced justice. Reckless rage endangered allies. Over time, natural selection favoured those who could calibrate their emotions to group harmony. In this sense, kindness was not the opposite of strength. It was its evolution. By 20,000 years ago, this emotional sophistication was visible in material culture. Cooperative projects such as large-scale hunting traps, communal shelters, and shared tool caches required coordinated labour and trust. These ventures were too complex for any individual or small family to manage. They represented an economy of mind as much as of resources. Behind each artifact lay countless invisible agreements: who would dig, who would carve, who would cook, who would guard. Every promise kept reinforced the neural scaffolding of civilization before civilization existed. At its deepest level, cooperation shaped identity. The individual became inseparable from the group. The I nested within the we. This cognitive shift is still one of anthropology's greatest puzzles. How did self-awareness, once the hallmark of consciousness, evolve to include others? Perhaps it began with mirror neurons, those cells that fire both when performing an action and when watching another perform it. Over time, these neurons may have extended their empathy from motion to emotion, making it possible to feel another's pain, joy, or fear as if it were one's own. The result was not just social intelligence, it was shared consciousness. This capacity for mutual awareness may explain why humans began to form moral intuitions long before moral systems. The same neural circuits that detect pain also react when we see someone else hurt. Fairness, compassion, and even sacrifice are not divine gifts, but evolved heuristics, biological shortcuts for surviving together. Our ancestors didn't philosophize about ethics. They lived it because cooperation was the most efficient form of selfishness ever discovered. Still, the picture is not one of universal harmony. Empathy's circle had boundaries. Genetic and ethnographic studies suggest that while cooperation flourished within groups, hostility toward outsiders often intensified. Trust evolved alongside suspicion. Unity required exclusion. The dual capacity for compassion and cruelty is, in many ways, the cost of being social. Evolution optimized humans for small interdependent networks, not for global empathy. Yet within those circles, the capacity for loyalty, love, and fairness reached unprecedented depth. The story of how kindness became power is, at its core, a story about feedback. Each cooperative success reinforced the neural and genetic patterns that made further cooperation easier. Over tens of thousands of years, these feedback loops built the emotional architecture of our species. By the time the ice began to retreat, humans were no longer just surviving through intelligence. They were surviving through connection, through trust systems encoded in hormones, emotions, and stories. And perhaps that is the quiet truth of evolution. The most successful species on Earth did not conquer by force alone, but by learning to care. Empathy became a weapon against chaos, wielded not to destroy but to endure. Why did trial and error become the human superpower? Somewhere in the long, uneven chapters of the Pleistocene, our species learned something most animals spend their entire lives trying to avoid: the usefulness of failure. For early humans, every tool chipped wrong, every hunt that went awry, every burnt meal or broken spear was not an end but an experiment. It was, in hindsight, the slow invention of learning itself. Long before we built civilizations, we built feedback loops. Imagine the first engineer who invented failure. Perhaps it was a tired hunter squinting at a stone core that kept shattering in the wrong direction. Or a woman testing a new kind of root over the fire, realizing too late that it smoked more than it cooked. Each mistake carried information, what not to do next time. Over generations, those errors became the foundation of adaptive intelligence. While other animals learned through instinct or imitation, humans learned through persistence. They turned frustration into data. The human brain is, in many ways, a prediction machine that survives by being wrong. Modern neuroscience has a name for this: predictive coding. Every perception, every action is a hypothesis about how the world should respond. When the world disagrees, when the spear misses, when the flint cracks the wrong way, a prediction error fires through the brain, strengthening or weakening synaptic connections until the next attempt aligns closer with reality. In the deep evolutionary past, this mechanism became the most efficient tutor the species ever had. The more mistakes we made, the faster we improved. Archaeological traces of this trial and error process are everywhere. The layers of debris at ancient tool sites often contain hundreds of discarded flakes and shattered cores, far outnumbering successful artifacts. In the earliest Acheulean hand axes, the ratio of waste to finished tools was enormous, but over hundreds of thousands of years the symmetry improves, the scars of failure shrinking as experience accumulates. The stone record, in its quiet way, is a diary of perseverance. Each imperfect tool is a thought in progress. By the later Pleistocene, this same learning pattern had moved beyond tool-making. Hunters adapted to shifting prey migrations not by instinct, but by experimenting, following tracks in new terrains, testing ambush points, adjusting strategies as herds learned to evade them. Cognitive scientists call this exploration-exploitation balance. You must risk exploring the unknown to find better outcomes, but not so often that you waste energy on chaos. Humans, perhaps uniquely, evolved a brain wired to tolerate uncertainty just long enough to benefit from it. Curiosity was no accident. It was adaptive gambling. The neural system responsible for this experimentation is ancient yet refined. Deep in the midbrain, the dopaminergic circuits that regulate reward and motivation began to favour not just success but improvement. Modern imaging studies show that the brain releases dopamine, the same molecule associated with pleasure, not only when we succeed, but when we realise we're learning. It's the neurochemical equivalent of a high five for trying again. Somewhere along the Pleistocene timeline, failure became addictive. This ability to find reward in progress, not perfection, may explain why humans never stopped tinkering. Archaeologists often find multiple overlapping designs of the same tool in a single layer, evidence of iterative development. A point slightly sharper here, a grip reshaped there. No one invented innovation outright. It was an emergent property of error. A broken spear tip could inspire a better hafting method. A burned meal could lead to the discovery of flavour. Even small mistakes had compounding benefits, feeding into what researchers call cumulative culture, evolution's version of patch notes. The process was messy, of course. Some errors were catastrophic. Misjudged cliffs, untested plants, poorly timed hunts. Each could end a life. But the survival of groups depended on how quickly they learned from loss. This is where cooperation again entered the system. Humans became not just individuals learning from their own mistakes, but species learning from each other's. Teaching and storytelling turned failure into a shared resource. Don't eat that root. Don't hunt near that river. Don't sleep where the wind changes. Wisdom in its earliest form was error prevention passed down around the fire. This social aspect of learning magnified the evolutionary power of failure. One mistake could teach 100 others. Genetic evolution could never compete with that speed. Once information began spreading horizontally, from person to person, not just from parent to offspring, every wrong step became a contribution to collective intelligence. By the later Ice Age, survival was no longer about avoiding mistakes, but managing them. Even anatomy reflects this shift. The human hand, with its precision grip and opposable thumb, became an organ not just of manipulation, but of feedback. The nerves in each fingertip send continuous information to the brain, adjusting pressure, angle, and motion. This fine motor control allowed for iterative correction within seconds, the physical basis for learning through doing. Stone knappers today describe entering a trance-like rhythm where each strike improves the next by feel alone. The brain and hand form a closed loop of error correction, an ancient symphony of calibration that defines craftsmanship to this day. Our ancestors likely applied the same feedback logic to problem-solving beyond tools, to navigation, fire-making, even social relationships. The emotional systems that register embarrassment or shame may have evolved as social analogues of physical pain, signals to adjust behaviour without repeating costly mistakes. In that sense, feelings themselves are biological error messages. Regret, awkwardness, or frustration are not flaws in the design. They are the design. They ensure that the lesson outlives the moment. From an evolutionary point of view, this was an elegant solution. Rather than rely on rigid instincts that might fail in new environments, humans evolved flexible learning guided by error sensitivity. The same neural circuits that once guided hand-eye coordination began shaping abstract reasoning. Hypotheses, tests, revisions. Long before the scientific method was formalized, the species had already internalized it. Every toolmaker was a miniature experimenter, every explorer a data collector. And through it all, humour may have played a role. Anthropologists studying modern hunter-gatherers often note how laughter diffuses tension after failed hunts or accidents. It turns error from threat into resilience. It's possible this social mechanism has deep roots, the Pleistocene version of "it's fine, try again." A group that could laugh together at failure would recover faster, innovate more, and bond more deeply. The first joke in that sense may have been about a mistake, and it probably saved lives. By the end of the Ice Age, humans had become creatures defined by their tolerance for failure. No other species has ever explored so recklessly or adapted so quickly to being wrong. Our ancestors did not master fire, stone, or ice through perfection, but through endless, patient experimentation. Every success was built on a graveyard of small defeats. Evolution didn't just shape smarter brains, it shaped braver ones, minds willing to try, fail, and try again in an indifferent world. Perhaps that is the real secret of the human story. We are not the species that always gets it right, but the one that keeps correcting itself until it does. Intelligence is not the absence of error. It is the art of recovery. What secrets are buried in our own DNA clock? Between 60,000 and 15,000 years ago, something subtle but extraordinary happened within the invisible machinery of our species. Beneath the surface of migration, toolmaking, and adaptation, human evolution was rewriting its own code. The changes were too quiet to leave fossils, too fast for the slow rhythm of deep time, yet their traces are still whispering in our genomes today. They are the molecular shadows of a species under pressure, tiny mutations that turn survival into acceleration. To understand this period, imagine the human genome as an ancient library, each gene a sentence, each mutation a letter change. For most of history, these edits happened at a glacial pace, but somewhere around 60,000 years ago the pace quickened. Geneticists call it an acceleration of the molecular clock, a measurable increase in the rate of new mutations spreading through populations. It's as if evolution stopped strolling and started running. Why it happened remains one of science's great enigmas. Mutation rates are influenced by many factors: population size, environment, lifespan, even cosmic radiation. Yet none fully explain the sudden uptick. One hypothesis suggests that as humans spread into new regions, they encountered novel climates, pathogens, and diets that applied fresh selective pressures. Each new challenge acted as a filter, rewarding genetic tweaks that offered even the smallest advantage. Another theory focuses on demography. When populations expand rapidly, rare mutations have a better chance of surviving drift and reaching fixation. The Ice Age, paradoxically, may have been both bottleneck and catalyst, culling some lineages while accelerating adaptation in others. When scientists compare DNA from ancient remains to that of modern humans, they can trace these accelerations like timestamps. Certain regions of the genome show unusually low diversity, a telltale sign of selective sweeps. That means a beneficial mutation spread so quickly through the population that it erased variation around it, dragging neighbouring genes along for the ride. Each sweep is a silent footprint of natural selection's invisible hand. During this period, dozens of such sweeps occurred, touching genes related to brain development, immune response, and energy metabolism. Evolution was optimizing us not for a single environment, but for adaptability itself. Among the most intriguing clues are the so-called introgression shadows. When our ancestors encountered other hominin populations, they didn't always compete. Sometimes they exchanged genetic material. Even without naming the partners, the evidence of interbreeding is unmistakable. Fragments of foreign DNA scattered through our genomes like faint echoes of vanished cousins. Some of these borrowed genes conferred advantages, improved immunity to local diseases, altered skin pigmentation, or adaptations to high-altitude living. Others linger as mysteries, sequences with no clear function but deep evolutionary history. We are, quite literally, mosaics of lost experiments. This blending didn't just diversify our biology, it altered the rules of mutation itself. Mixing distant lineages can destabilize previously balanced gene networks, unleashing new combinations of traits. Some may have been harmful, others transformative. Evolution thrives on such chaos. It's possible that this genetic turbulence, hybridization followed by rapid expansion, triggered the very acceleration researchers observe in the molecular clock. Our ancestors may have stumbled into evolution's version of a feedback loop, diversity fueling adaptation, adaptation enabling further diversity. The most striking changes during this window appear in genes linked to neural development. Regions like HAR1, ASPM, and microcephalin show evidence of rapid alteration, suggesting selection for brain wiring rather than size. These genes influence how neurons proliferate and connect during fetal growth, subtly reshaping the architecture of thought. What drove this? Perhaps social complexity. The demands of cooperation, deception, and memory favoured brains that could handle more nuance, or perhaps environmental volatility rewarded cognitive flexibility. Whatever the cause, evolution began optimizing not for intelligence in the abstract, but for adaptability under uncertainty. Yet even as selection sculpted the mind, other systems evolved in tandem. Genes related to diet, such as those regulating starch digestion and fatty acid metabolism, show parallel adaptation, reflecting dietary diversification across continents. Immunity genes also bear the scars of conflict, with ancient variants still influencing susceptibility to modern diseases. Each adaptation tells a story of confrontation between biology and circumstance, of a species learning to survive by constantly rewriting its own instructions. Geneticists can even measure the tempo of these changes using molecular clocks, techniques that estimate how long ago mutations arose based on known rates of DNA replication errors. When they map these onto timelines, a curious pattern emerges. Many of the most consequential mutations in human evolution cluster within this narrow window of late Pleistocene time. It's as if, for a brief geological moment, evolution's metronome skipped a beat. The genome went from static to restless, encoding a species that would never again stay still. The reasons may also lie within the machinery of mutation itself. Studies suggest that stress, temperature extremes, and nutritional strain can influence DNA repair mechanisms, subtly increasing mutation rates. The harsh oscillations of Ice Age climates could have made our ancestors both vulnerable and inventive, their cells under constant pressure to adapt. Even the increased longevity of modern humans may have played a role. Longer reproductive spans give natural selection more generations to experiment with small changes. There is humility in this story. The mutations that define us were not deliberate improvements, but accidents that happened to work. Evolution is not a sculptor with a plan. It is a tinkerer with a limitless supply of errors. Most genetic changes did nothing or caused harm, but occasionally one aligned perfectly with circumstance. A slightly faster neural firing rate, a more efficient enzyme, a more resilient immune response. Over thousands of generations, these rare alignments accumulated, gradually rewriting the blueprint of our species. And while the past left its record in fossils and tools, the genome is its secret diary. Each person alive today carries molecular relics of that era, silent witnesses to a time when the pace of change quickened. In our cells, ancient signatures still linger, alleles tuned for Ice Age diets, for ancient pathogens, for environments that no longer exist. We are, in a sense, time travellers carrying the biological software of people who lived through unimaginable climates and migrations. Modern genetics continues to reveal how profound that acceleration was. By comparing the DNA of contemporary humans across the globe, researchers have identified hundreds of regions that underwent recent positive selection, many within the last 40,000 years. These include not only physical traits but regulatory sequences, switches that control how genes turn on or off. It seems evolution began working smarter, not harder, refining expression rather than structure. The genome was learning efficiency. What remains uncertain is whether that acceleration ever truly stopped. Some geneticists argue it continues today, subtly reshaping our biology in response to modern pressures. Urban life, new diets, new diseases. If so, then the story of the hidden mutations isn't ancient at all. It is ongoing, written every time a cell divides. Perhaps the most haunting realization is that we carry within us the memory of change itself. Every heartbeat, every breath, every thought is supported by genetic improvisations tested by time and chance. Evolution's quiet genius was not in perfection, but in persistence, in the willingness to keep mutating until something worked. The hidden mutations of the late Pleistocene didn't just make us human, they made us unfinished. How fast can a culture double its intelligence? After 40,000 years ago, something remarkable began to unfold across the world, not in anatomy or genetics, but in information itself. Knowledge, once confined to the pace of human memory, began to move through space and time with the speed of a rumour. Ideas were no longer reborn with each generation. They were copied, refined, and multiplied. In the silence between continents, a global network of learning was forming long before the first cities or alphabets. Humanity had discovered the physics of information, and it was accelerating. Archaeologists once imagined ancient progress as slow and local, but the material record tells another story. The same tool forms, ornaments and techniques appear thousands of kilometres apart within a few centuries, an eye blink on evolutionary scales. Blade industries, once regional, spread across entire continents. Specific flint knapping styles in France mirror those found on the Russian steppe. The design of projectile points migrates from Central Asia to Europe with astonishing speed. Something invisible was connecting minds. How fast was knowledge moving? When researchers model the spread of technological innovations through prehistoric populations, the results are startling. Even at densities as low as 1 person per 10 square kilometres, innovations could diffuse across a continent within a few hundred years through overlapping exchange networks. Each tribe functioned as a node in a vast information web, trading not just goods, but memory. The earliest global system was not political or economic, it was cognitive. The key to this network lay in redundancy and repetition. Ideas were robust because they could travel through multiple routes. A flint knapping technique might pass eastward via trade, westward via migration, and northward via imitation. 3 parallel data streams ensuring the survival of the method, even if one group vanished. Knowledge became self-replicating, resilient to time and disaster. The same redundancy that makes modern digital systems reliable was already emerging around Paleolithic hearths. This is where physics meets culture. Information, like energy, follows laws. It spreads when channels are open, decays when they're closed, and accelerates when feedback loops form. Around 40,000 years ago, those loops appeared everywhere. Trade routes linking river valleys, seasonal gatherings at resource-rich sites, long-distance marriages connecting clans. Each contact point multiplied the potential for transmission. The cultural bandwidth of humanity was expanding. Take, for instance, the diffusion of raw materials. At sites in Central Europe, shells from the Mediterranean, pigments from distant mountains, and exotic stones from faraway quarries appear side by side. These materials were not transported by single individuals making epic journeys. They moved through chains of exchange, each step carrying information about its source, its value, and its use. Every traded object was also a data packet, proof that someone, somewhere, knew more. Mathematically, this creates what network theorists call a small world structure, where even sparse connections can transmit complex information efficiently. In such systems, local clusters remain tight but are bridged by a few long-range links, the prehistoric equivalent of the modern internet backbone. A bead carved in one valley could influence fashion in another 1,000 kilometers away. A new blade design invented in one shelter could become standard in a dozen generations across half a continent. The power of this network was not just in speed, but in memory retention. When knowledge circulates widely, it becomes harder to lose. One group's forgetfulness can be offset by another's recollection. Cultural memory thus behaves like a distributed database, decentralized, redundant, and remarkably durable. Even if a population collapsed, its inventions could persist in neighboring groups. The continuity of technologies such as pressure flaking, compound adhesives, or fiber weaving suggests that humanity had achieved informational immortality long before writing. Archaeologists studying this diffusion often use analogies from epidemiology. Ideas behave like beneficial contagions. A useful innovation, say a more efficient spear point or a new pigment mixture, spreads not randomly, but according to the structure of contact networks. Denser populations accelerate the process, but so do travelers, seasonal migrations, and shared rituals. The physics of innovation obeys no borders, it follows connection. From a cognitive perspective, this acceleration created feedback between learning and invention. As ideas spread faster, they recombined more often. A single innovation could encounter another thousands of kilometers away and merge into a hybrid. Each merger created exponential growth in possible combinations, a combinatorial explosion of creativity. The human brain had already reached its modern capacity. What changed was how many other brains it could interact with. Intelligence stopped being individual and became collective. We can glimpse this collective mind in the archaeological record through sudden bursts of technological diversity. Between 40,000 and 30,000 years ago, for example, we find simultaneous surges in bone tool specialization, pigment chemistry, and projectile design across multiple continents. These are not isolated coincidences. They represent network effects, the signature of knowledge passing a critical threshold. Once enough connections existed, culture began evolving faster than climate, faster even than biology. This acceleration also reshaped social behavior. Maintaining information flow required sustained contact and trust. Trade routes became not just economic corridors, but arteries of communication. To keep them open, humans developed shared conventions, weights, measures, symbolic tokens. These were the world's first protocols, establishing reliability across distance. The need to preserve accuracy over transmission may even have laid the groundwork for later abstract reasoning. Counting, pattern recognition, and categorization all thrive where fidelity matters. At a deeper level, information transmission likely influenced brain wiring. Neuroplasticity ensures that frequently practiced skills strengthen the underlying circuits. A species constantly exchanging, imitating, and adapting would, over millennia, reinforce networks for pattern detection and learning. The brain evolved not for solitude, but for synchronization. Each interaction became both data exchange and mental calibration, aligning one mind's rhythm with another's. When scientists today map the spread of early innovations using computer simulations, they find that culture behaves less like a tree and more like a web, tangled, recursive, impossible to separate into clean lineages. This is why archaeology sometimes finds the same technology arising independently in distant regions. Innovation is rarely singular. Once a network is dense enough, ideas become inevitable. It is tempting to see this acceleration as progress, but evolution has no finish line. The same connectivity that preserved knowledge also made societies vulnerable to collective error. A bad idea could spread as efficiently as a good one. The physics of information has no moral filter. It rewards transmission, not truth. Yet even this vulnerability contributed to resilience. The ability to test, discard, and refine, to manage the noise of one's own inventions, became another layer of adaptation. By 20,000 years ago, the human information web spanned continents. Without writing, without wheels, without cities, knowledge was already global. The diffusion of ideas across these invisible routes prefigured every later system, from trade empires to digital networks. What began as whispers around fires had become a planetary murmur, self-sustaining and self-correcting. If intelligence could be measured not by neurons but by connections, then this was the moment humanity became super-intelligent, not because individuals were smarter, but because ideas began to move faster than they could die. The species had achieved a kind of cultural escape velocity. From then on, information would no longer wait for evolution. It would become evolution. Did the Red Queen just change arenas? 10,000 years ago, the great evolutionary race that had once been fought against predators, climate and scarcity began to pivot toward a new front, humanity itself. The glaciers withdrew, the grasslands stabilized, and the world briefly stopped trying to kill us. But instead of slowing down, we accelerated. The competition that once sharpened our tools now began sharpening our societies, our ideas, and our ambitions. The evolutionary arms race had moved inside the species, from the savannah to the village, from the wilderness to the mind. For hundreds of thousands of years, survival meant adaptation to nature's moods. But around 10,000 years ago, as the climate calmed and wild game thinned, groups of Homo sapiens began to manipulate their surroundings instead of chasing them. The domestication of plants and animals marked a shift so profound that it rewired the rules of evolution itself. Agriculture did not emerge as a single discovery, but as dozens of parallel experiments scattered across the planet. Wheat and barley in the Fertile Crescent, millet and rice in East Asia, yams in West Africa, maize in Mesoamerica. Each was a local answer to the same global equation. Too many mouths, not enough wild food. What followed was not peace, but pressure. Farming allowed more people to survive, which in turn demanded more food, which required more farming. It was the same Red Queen dynamic, now transferred from ecosystems to economies. We had to keep running, not to stay alive, but to stay fed. Archaeologists tracing early agricultural layers often describe the pattern as a feedback loop, a self-reinforcing spiral of cultivation and population growth. The same process that stabilized food production also created inequality, territorial defense, and hierarchy. The Red Queen had not vanished. She had simply changed costume, now wearing the robes of civilization. The new race favored new traits. Where Ice Age hunters needed mobility, farmers needed endurance. Where foragers prized adaptability, agricultural societies prized specialization. Tools multiplied again, not for survival in nature, but for efficiency within culture. Sickles, grinding stones, irrigation channels, and granaries appeared across the archaeological record. Each was an instrument of productivity, but also of competition. A better plough meant more grain meant more influence meant more allies, more offspring, and ultimately more survival. Evolution's stage had expanded from genetics to economics. As villages grew, they became laboratories of social complexity. Cooperation, once limited to bands of a few dozen individuals, now had to scale to hundreds, then thousands. The human brain, already optimized for face-to-face interaction, faced a new challenge: abstract coordination. People began organizing around symbols, myths, and authority, shared fictions that allowed strangers to cooperate. Religion, law, and ritual became the new cognitive software enabling large-scale societies. From an evolutionary standpoint, these belief systems functioned like neural networks linking vast populations into synchronized behavior. Archaeological sites such as Çatalhöyük in Anatolia and Jericho in the Levant reveal this transformation in clay and stone. These early proto-cities were not simply collections of homes, they were social engines. dense clusters of information, hierarchy and control. Walls, storage rooms and communal spaces tell a story of growing interdependence. Every new innovation created both opportunity and pressure. A community that failed to adopt irrigation or metal tools risked being overtaken by one that did. Culture had become an arms race, and with it came an acceleration of inequality. For the first time, stored resources could outlast the individual. Grain became wealth, livestock became currency, and ownership became a genetic advantage. The social environment began to select not for physical strength, but for abstract intelligence, strategy, persuasion, and cooperation. Those who could navigate complex alliances, anticipate human behaviour, and exploit emerging hierarchies passed on their genes and their ideas. In a sense, evolution had delegated its process to culture. Instead of mutations, there were inventions. Instead of natural selection, there was social selection. This internalization of competition also reshaped human psychology. Where earlier pressures favoured endurance and adaptability, settled life encouraged anxiety, vigilance, and ambition. A hunter could move when resources failed, a farmer could not. Success now depended on predicting the future, the weather, the harvest, the mood of neighbouring tribes. The invention of planning as a survival mechanism may have intensified the very cognition that once arose from linguistic recursion tens of millennia earlier. The same mind that imagined mammoth hunts now imagined tax collection, irrigation schedules, and future wars. From an energy perspective, agriculture also marked the beginning of externalized metabolism. Instead of relying solely on calories gathered or hunted, humans began harnessing the energy of landscapes, animals, and later, metals. Each innovation expanded the carrying capacity of land but demanded more coordination and control. Villages turned into city-states into empires, each one a complex organism requiring constant adaptation. The Red Queen had grown larger, faster, and hungrier. The archaeological record mirrors this expansion in breathtaking detail. Between 10,000 and 5,000 years ago, pottery styles, metalwork, and architectural innovations spread at a rate rivaling the earlier diffusion of Paleolithic tools. Where once obsidian blades had crossed mountain ranges, now bronze and copper crossed entire continents. Knowledge began moving through trade caravans and river systems rather than small bands of migrants. Information flow became institutional, recorded, stored, and protected. Writing, which emerged around 5,000 years ago, was not a sudden leap but the culmination of this long cognitive spiral. Clay tokens used for accounting evolved into marks, then symbols, then full scripts. What had once been stored in memory now existed outside the brain. Humanity had invented external cognition again, this time not in stone blades but in clay tablets. Each inscription was an insurance policy against forgetting, a safeguard in the race to manage increasingly complex societies. But progress carried its own cost. The same cooperative systems that allowed agriculture to flourish also intensified conflict. The ability to coordinate thousands of people made peace possible, and organised war inevitable. Resource control, territory and ideology replaced predators as the dominant selective pressures. The evolutionary arms race had become geopolitical, yet even here the old logic persisted. Adapt or disappear. Groups that developed better strategies for defence, diplomacy or logistics thrived. Those that did not left only ruins. From a biological perspective, humans may not have changed much since the late Ice Age, but culturally the acceleration never stopped. Each new layer of complexity demanded another layer of cognition, record-keeping, administration, abstract reasoning. The result was a cascade of innovation built not from need, but from necessity's shadow, competition. Civilization was not the end of evolution, it was its reconfiguration. The Red Queen had simply traded her running shoes for sandals. Even in this new world of harvest and monuments, the principle remained the same. Every advantage created pressure for the next. Irrigation demanded mathematics. Mathematics demanded writing. Writing demanded bureaucracy. With each invention, humanity bound itself to its own momentum. The race had turned inward, but it had not slowed. It merely changed form, from the race of survival to the race of understanding. And somewhere in this long recursive loop, we began to glimpse the cost of our acceleration. The same intellect that tamed rivers and stored seasons also began to ask, where does this end? Evolution had found a new way to run, not through mutation or climate, but through the restless architecture of its own mind. And in the quiet between each new breakthrough, there was always the faint echo of the same rule whispered since the Pleistocene. To stay in the same place, you have to keep running. Can evolution keep up with what culture built? In the long race of adaptation, our species found a way to outpace almost every rule nature had ever written. But in doing so, it may have left something behind, itself. Over the last 10,000 years, our inventions have changed faster than our biology can follow. The same brain that once mapped herds on a tundra now navigates cities, screens, and schedules. The same stress that once helped us survive a predator now fires endlessly over an email or a thought. The story of the Holocene to the modern age is not only about progress, it's about the growing space between what we are and what we've made. The concept scientists now call evolutionary mismatch begins here. Evolution optimizes slowly over millennia, tuning species to the pressures of their environment. Culture, on the other hand, mutates almost overnight. When a species creates an environment faster than genes can adapt, the old survival strategies start misfiring. What once kept us alive now makes us sick, restless, or overwhelmed. Evolution is still running, but the track has changed shape. The human nervous system, sculpted for scarcity, still reacts to abundance as if it were danger. The sight of food triggers ancient reward circuits. In a supermarket, that system becomes chaos. The stress hormone cortisol, designed to surge briefly during a hunt, now lingers for years in the bloodstream under the constant micro-pressures of modern life. Anxiety, depression, and burnout, terms born in the 20th century, are, in a deeper sense, evolutionary ghosts. They are the sound of instincts searching for problems that no longer exist, and finding new ones to replace them. Our sleep, too, carries this lag. For most of human history, darkness meant rest, reflection, or silence. Now, electric light has torn that rhythm apart. The pineal gland, once perfectly synchronized with the sun, struggles to measure time under artificial skies. Blue light suppresses melatonin, circadian cycles fracture. The body's ancient sense of night and day becomes blurred into one long fluorescent twilight. The result is a global species constantly half awake, creatures of daylight still trying to live in a world that never darkens. The mismatch extends beyond physiology. The human social brain evolved in small bands, 50 to 100 individuals. That was the number of relationships we could manage, remember, and trust. Civilization expanded that circle to thousands, then millions, then billions. Each new layer of contact widened the network, but thinned the intimacy. Our ancestors evolved oxytocin-driven empathy for faces they could touch and voices they could hear. Now, we negotiate emotions through symbols on screens. The same neural systems that bound us together in the Ice Age now trigger loneliness in the crowd. And yet, this isn't a condemnation. It's an observation of scale. Culture grows exponentially, evolution inches forward. The distance between those speeds defines modern humanity, a species suspended between biology and invention. For all our achievements, our bodies still belong to the Pleistocene. The heart that races before public speaking, the tears shed over imagined losses, the hunger for belonging. These are Ice Age tools used in a neon maze. The paradox is that this lag also sustains creativity. The friction between what we were built for and what we build now forces continuous adaptation. Each mismatch becomes a new problem to solve, a new story to tell. From an evolutionary lens, stress is information, the body's way of saying the world has changed again. What we call anxiety might, in some cases, be the echo of adaptation still underway. But the cost remains. Chronic stress rewires the brain's reward system, dampening joy and learning. Constant alertness dulls focus. Immune systems trained for infection now turn inward, creating inflammation, allergies, and autoimmune conditions. Even our skeletons carry traces of this mismatch. Shorter bones, weaker joints, smaller teeth, all products of lifestyles that diverge from the rhythms of hunting and foraging. Biology is still catching its breath while culture keeps running. Perhaps the most striking mismatch is psychological. In the Paleolithic, achievement meant survival. A hunt completed, a child grown, a season endured. Now, achievement has no endpoint. The race has no finish line. The same motivational circuitry that once ensured persistence now fuels endless striving. Dopamine, the molecule of anticipation, floods systems designed for periodic reward but now overstimulated by constant novelty. The result is a species addicted to progress, unable to stop moving even when safe. Anthropologists sometimes describe this as the human tragedy of success. Our ancestors' ingenuity removed so many natural dangers that the brain turned inward to find new ones. We began competing not with predators, but with expectations, ideals, and ourselves. Evolution didn't prepare us for comfort, it prepared us for challenge. And so, even in comfort, we invent challenges to stay engaged. The marathon continues, only now the terrain is psychological. Still, it would be wrong to call this a failure of evolution. Evolution is indifferent. Its goal is not harmony but persistence. The fact that we are here, stressed, sleepless, and conscious of it, is proof that, for all the mismatch, the system still works. But it is changing again, faster than ever. Our brains, wired for slow embodied learning, now live amid data streams and abstract systems that shift daily. We are adapting, but not evenly. Some thrive in the noise, others drown in it. This dissonance reveals something profound. Adaptation is not just about survival anymore. It's about coherence, the ability to remain stable while everything else accelerates. From an evolutionary standpoint, that may be the next frontier. The future may not favour the strongest or smartest, but those most able to stay balanced in turbulence. For now, the evidence remains humble. Geneticists can trace subtle, ongoing selection for stress resilience, metabolism, and immunity. Psychologists track new cognitive strategies for managing information overload. Neuroscientists observe brains developing shortcuts for pattern recognition in chaotic environments. We are still running, but perhaps beginning to pace ourselves differently. If earlier evolution was about running to survive, this phase might be about learning when to stop. In a world that no longer waits for the slow rhythm of mutation, wisdom may become the new adaptation, the choice to rest before the next sprint. Because even the Red Queen, in Lewis Carroll's tale, pauses to remind Alice that endless running only keeps one in place. The challenge now is not speed, but direction. Are we competing with ourselves or our inventions now? For most of our history, the race was external. Predators, famine, rival tribes. Then it became internal. Societies, hierarchies, and the restless churn of progress. But somewhere along the line blurred. The Red Queen, that ancient symbol of relentless adaptation, now stares back from our own reflection. In the age of information, our primary competition isn't nature or even one another. It's the systems we've built to amplify our minds. And like all evolutionary games, this one carries both brilliance and cost. The modern human lives inside a cognitive arms race of their own design. Each advance in technology multiplies the channels of attention while compressing the time to process them. Our nervous system, a product of slow biological sculpting, now navigates a torrent of signals it never evolved to handle. Notifications, data streams, headlines, messages. They all compete for the same limited circuitry once reserved for survival cues on a savanna. The predator has changed shape. It doesn't chase us anymore, it pings us. From a neurobiological standpoint, this is an unprecedented stress test. The brain's reward network, shaped to release dopamine for discovery and novelty, now fires continuously under the constant stimulation of information. Psychologists call it intermittent reinforcement. The same mechanism that kept our ancestors scanning the horizon now keeps us refreshing screens. Each new piece of input promises potential reward, a message, an insight, a warning. The brain, ever vigilant, keeps running. But the finish line has dissolved. This dynamic mirrors the logic of the Red Queen perfectly. Every technological leap forces us to adapt just to stay functional. Faster devices demand faster cognition. Smarter algorithms demand smarter filters. Each convenience extracts a little more attention, which becomes the new resource in competition. In evolutionary terms, we are witnessing the emergence of a new ecological niche, not defined by geography, but by mental bandwidth. Those who can manage overload thrive, those who cannot falter. Anthropologists studying the cognitive load of modern life sometimes liken our situation to an energy crisis of the mind. The human prefrontal cortex, responsible for decision-making and focus, consumes enormous metabolic resources. In ancestral contexts, this system was active in bursts, moments of planning, hunting, or storytelling. Now, it's permanently switched on. Every alert, every decision fragment, every piece of micro-information consumes fuel. Fatigue follows not from physical labour, but from the ceaseless requirement to choose. This phenomenon, cognitive overload, represents a subtle but profound evolutionary tension. Our tools, designed to extend the mind, now outpace the limits of the biological substrate. What began as amplification becomes interference. Researchers in neuroscience call it the paradox of augmentation. The more we extend cognition into technology, the harder it becomes to distinguish between tool and task. The Red Queen now runs on silicon legs. What's striking is that this process feels natural because it follows the same logic as cultural evolution itself. Innovation has always been cumulative, each new layer built atop the last. The difference now is tempo. Whereas Stone Age tools diffused over millennia, digital ideas replicate globally in seconds. The feedback loop that once shaped flint now shapes thought itself. Every scroll, click and search becomes data for systems that learn and adapt faster than the biological users feeding them. Evolution hasn't stopped, it's been outsourced. But again, not all consequences are dire. Adaptation cuts both ways. Humans are remarkably flexible, and even within a generation, patterns of cognition begin to shift. Studies of memory show that the brain reorganizes when external storage becomes reliable. We forget differently now, not less, but strategically. Rather than storing facts, we store pathways to them. Our ancestors memorized landscapes and seasons. We memorize where to find information about them. From an evolutionary perspective, this is still intelligence, just distributed differently. Still, the cost is measurable. Attention, once a survival tool, is now currency. Economists even call it that, the attention economy. Every sound, colour and word designed to capture it must outcompete others doing the same. This constant contest reshapes our perception of time. Hours dissolve into fragments, each filled with microbursts of stimulation. The result is what psychologists describe as temporal myopia, the shrinking of the mind's future horizon. When attention fragments, planning collapses. The same capacity that once allowed humans to imagine years ahead now struggles to imagine a quiet minute. This cognitive compression doesn't mean we are weaker, only that the conditions have changed faster than selection can respond. The brain's ability to adapt across a single lifetime, its plasticity, offers resilience, but at a cost of restlessness. To cope with this speed, we unconsciously outsource cognition to the very tools that accelerate it: calendars, reminders, feeds. Our minds extend across devices and platforms, creating a hybrid intelligence that feels seamless yet slightly alien. The self now spans flesh and circuitry, but evolution has not yet reconciled the boundary. If the Red Queen once symbolized survival through motion, her reflection today represents survival through adaptation to one's own inventions. The human-machine feedback loop is not a war but a negotiation, one that tests how far biology can stretch before it begins to fracture. Our species has always lived in this tension between extension and dependence. Fire warmed us, but burned us. Writing preserved memory, but replaced it. Every tool grants a new ability and takes something back. Scientists observing the neuropsychology of constant connectivity often describe modern stress not as fear, but as fragmentation. The stressor is not danger, but density. Too much input, too little silence. And yet, within that noise, humans continue to find meaning. We curate, we filter, we create hierarchies of relevance. Perhaps this too is an adaptation in progress, a mental immune system learning to distinguish signal from noise. Viewed through the lens of evolutionary psychology, The modern world is simply the latest iteration of an ancient process. Competition, not for survival, but for attention, influence, and coherence. Every era of humanity has had its own battlefield. For hunter-gatherers, it was nature. For farmers, the soil. For industrialists, the machine. For us, it is cognition itself, the space between thought and interruption. The battleground is invisible, but its stakes are immense, and yet humility remains our best adaptation. We do not fully understand what this acceleration means. We can only observe the patterns forming, much as early naturalists once observed migration routes or fossils. From that vantage, one truth persists. The Red Queen never disappears. She simply finds new ways to make us move. This time, she runs inside our own reflection, urging us forward not through threat but through fascination, through the endless urge to know, to connect, to keep up. If the race never ends, what are we really running toward? Every generation of our species has asked this question in its own language, in songs, in stone, in silence. From the first spark struck in the dark to the circuits glowing around us now, the story has never been about the finish line. It has been about the running itself. The rhythm that began in the ancient genome, adapt, survive, change, still hums beneath everything we do. We were never meant to win this race. We were meant to understand that running was the point. Looking back across the ages, it is difficult not to be awed by how far this motion has carried us. The first humans watched the horizon for danger. The last ones watched the horizon for meaning. Between them, a single thread: curiosity. What began as vigilance became imagination. Every adaptation we invented, from tools to tribes to theories, started as an act of curiosity under pressure. Each step we took to survive made us more capable of asking why we wanted to. The struggle built the question. Competition, in the end, gave birth to cooperation. The logic of the race was never pure conflict. It was the refinement of connection. The same pressures that forced us to sharpen stone also forced us to share it. We learned to build alliances not to dominate nature, but to stay alive within it. The rivalries that shaped our history also shaped our empathy. The more we understood how to outthink one another, the more we learned the cost of doing so. In that tension between competition and compassion, something extraordinary appeared. Intelligence with memory. For all our speed, what truly changed the world was not strength, nor even cleverness, but the decision to keep what we learned and pass it forward. Knowledge became our survival mechanism. Unlike any other species, we evolved not just to adapt, but to remember adaptation itself. Each discovery became a bridge across time: fire, language, writing, science. Each one carrying a memory of the last. Humanity did not escape nature. It became nature reflecting on itself. That reflection is the quiet miracle buried inside our restlessness. The race that began with movement through landscapes now continues as movement through understanding. We no longer run from predators, but from ignorance, from entropy, from forgetting. Yet, in every field, in every invention, the same ancient impulse whispers beneath the noise: keep going. Learn faster than you vanish. It is easy to mistake this momentum for chaos, but perhaps it is continuity. Evolution has always been improvisation with memory, a universe learning what works. When we study fossils, genomes, or histories, we are watching time experiment with intelligence. Every extinction and every birth is part of that experiment's rhythm. Life does not move forward with purpose, it explores until it finds coherence. And in that sense, humanity is one of its most intricate attempts yet, a lineage that made awareness recursive, so that evolution could finally look back and see its own footprints. To realize that is to understand that the race never truly left the savannah, or the cave, or the laboratory. It only changed terrain. Each era built upon the one before it, layering complexity upon simplicity, until thought became its own environment. The result is not a hierarchy of progress, but a widening of perspective. The same selective forces that once favoured better eyes or stronger legs now favour better questions. Curiosity itself became adaptive. There is humility in that idea. For all our technological grandeur, we remain participants, not masters. The systems we build still follow the same principles written in DNA: feedback, replication, variation, and survival through resilience. Every innovation we celebrate, from the first spearhead to the space telescope, follows that grammar of adaptation. When viewed across deep time, civilization looks less like an escape from nature and more like its continuation in another form. And perhaps this is what the race was always about. Not the conquest of the world, but the reconciliation with it. The more we understand about the mechanisms that made us, the less separate we become from the processes we once thought we controlled. Every discovery collapses a boundary between human and animal, mind and matter, past and future. Evolution, it turns out, is not a ladder but a mirror, one that reflects both our origins and our direction, showing us that progress and awareness are the same phenomenon seen from different sides. We may never know where this current leads, but in the quiet of that uncertainty lies a kind of peace. To exist as a species aware of its own unfinished story is not a flaw, it is the highest state evolution has yet achieved. The race never ends because the finish line keeps moving, expanding outward with every thought, every breath, every act of learning. The running itself is what keeps the species alive. When we look at the night sky, we're still those same apes gazing from the mouth of a cave, seeing reflections of our own fire scattered among the stars. The distance between then and now is measured not in years but in understanding. What we have built is not an empire or a technology, but a continuity of awareness. One mind stretched across millions of lives, learning, forgetting and remembering again. So perhaps the question is not what we are running toward, but what we are running from. The answer may be simpler than we think. Extinction, stagnation, the silence that comes when curiosity stops. To stay in motion is to stay alive, not in the biological sense, but in the cosmic one, as participants in the ongoing experiment of consciousness. And when the race feels endless, when the noise of progress grows too loud, it helps to remember what the evidence still whispers, that the point was never to win, but to learn how to keep running without losing our breath, to keep asking, even when the answers fade, to recognize that evolution, at its deepest level, was not about survival, but about self-awareness emerging from the long patience of the universe. If the Red Queen could speak now, she might smile, not in victory, but in recognition, because in the mirror she would see what she'd been running beside all along, us. Thank you, fellow sapiens, for wandering this timeline with me, for drifting into deep time, for slowing down and remembering. If this helped you fall asleep, helped you study, or simply helped you step out of the noise for a while, thank you for being here. If you think more people should know this story, you know what to do. Like, subscribe, share it with the sapiens in your life, and tell me, are you listening before bed, while working, or somewhere in the world I can only imagine? And as always, stay curious, stay calm. I'll see you in the next story.